Alright, supposedly I'm streaming and I'm going to go to full screen mode. Alright. Let me know when you see something. You should see something.
Yep.
Awesome.
Yep. See Jupiter.
Alright, you also see my cursor. That's good. Alright, good. Now, I have to just get... I need my observing list piece of book here, and that should be fine. Alright, cool. So I think my volume's coming across. Is everybody hearing me okay? I don't know how many people are probably...
Just remember, get as close to that microphone as possible, otherwise it's going to sound like you're in a hollow room.
I am in a hollow room.
That's true.
Yeah. So I apologize for that. I'm waiting for a longer cable for this mic, and that will change everything once I get that.
Yep.
Right now I don't have it, so I'm stuck doing this. I'm being as directional as I can though with the mic, so I apologize ahead of time for any difficulty hearing me. I'm adjusting the mic as best I can. I know this sounds the best, but that means I have to be too close to it and away from the telescope, and I can't do that. I can't actually see any of the chat. I'm just looking at the live view. So, I don't know if there's anybody in yet.
Yeah, there's quite a few people in there right now.
How many are in now?
I'd say at least 11.
Okay.
16.
Alright, well, look. This is the first inaugural live stream of the SkyTour LiveStream. And tonight we're going to be exploring some objects in the sky as I see them here, and where possible, I will show you using a planetarium program that I'll intersperse into the stream that shows where we are looking. I may do that either at the end or throughout, but there's some experimentation going on here. I never thought about using the planetarium program until tonight, and so I will give it a shot and see what we get. But
you have 23 right now.
Thanks, because you're also talking to everybody as well.
Yeah.
That's fine. So anyway, this obviously is Jupiter. I'm using it as a test just so I can get my focus, get the focus for the camera and everything, and so it's looking pretty good. I opened up the dome about a couple hours ago just so that I could get all the air out of here and get the equalized temperature going, because that's very important. You have to have equalized temperature in a dome, because you can't view without you cannot view if you have a problem with the temperature.
Now, you got the Sony A7S connected, correct?
I do. I have the A7S, and you can see the telescope's tracking very well. I mean, I'm not touching it.
It is. Now, is there any way to clean up the image a bit?
Clean up the image. Oh, you know what? Yes, of course there is. As I'm thinking about it, I'm not even paying attention to the fact that I've actually got this, and I'm going to drop out of the high view right now. I'm actually able to drop this way down to here, at least, which is there, and that's about 100, and then I can actually decrease the exposure to the point, and then I can increase there. That looks a little better. You can see some more detail, yeah?
Now I got a question for you. Once you get this in a nice crispy image, is there a way that you can zoom in with the A7S to blow it up more?
This is the A7S doing the zooming.
Okay. Gotcha.
Yeah. Now, I'm not doing eyepiece projection right now, which is where you take an eyepiece like you normally look through with your eye, and then what you do is you actually you put it in the telescope ahead of the camera, and then you put the camera to that, like the camera's your eye. And I have an eyepiece projection system here, but I'm a little disappointed in the actual appearance and the way it's working. So it's not as good for me. I don't like it. But what I want to do now is, I know that Keith is streaming the moon, and in a show of support, I'm going to go over to the moon as well. So what we're going to do is we're going to go on the handset here. We're going to pick the solar system, and we're going to go to the moon, and it's going to calculate where the moon is, and then we can just say go to, and you'll see the view change. Now I'm going to come back out to the wide view here on the telescope. Oh, that's the highest. Haha. Okay, sorry.
Now, I got a question for you, because I used the eyepieces today with the Sony A7S. Is there any way that you can put the eyepiece? Do you have that adapter to put the eyepiece tube? Oh, that looks better.
Yeah, I know. I actually, I had one more level of magnification I could go to with the A7S. I'm sorry. And the nice thing is, if you notice, you can actually see the Galilean satellites to the left there, as well as the detail on Jupiter. So this is a function of the telescope and how you manage the optics. And so I'm able to show both, which is kind of cool. I can also remotely focus, which I'm going to do right now. And you'll see how it's getting fuzzy. And then when I bring it back in, I actually have really, really tight control over the focus. You know, so that's really focused. And that's pretty good.
Remember, I'm seeing a delay on YouTube for 30 seconds, so it takes a few seconds.
I know.
Gotcha.
But my voice is going to come out at the same time that I'm talking on YouTube, correct? So we're going to get that same delay. And you're going to get that same delay. So we're talking about things that you're waiting to see, all right? But you're going to say, remember, I think you're going to say, remember, my picture's delayed. But meanwhile, it's already done its thing. It's already done what it's supposed to, I believe.
Remember, what you're seeing on OBS on your screen is real time. You remember, and even though I'm talking to you, that's real time, because you're looking at it in real time. So I'm seeing the image on YouTube 30 seconds after you're seeing it in real time on your screen right now.
That's true, because I haven't used. I'm using Skype to do the communication.
Right.
I'm not using OBS with a data segment. I'm sorry, that's my fault. Okay, yes, that's correct. All right, we'll get these things straightened out. Not a big deal. Saturn is rising according to my little alert here. But all right, let's see if I can go to the moon real fast. Okay, that's the sound of the telescope slewing over to the moon. And here it comes. Hang on one second. Wow. See? Now, this is what I wanted to talk about with my with this stream. The nice thing is, okay, it looks a little washed out. So you say, oh, that's kind of not that good. I don't really like it. It's a little washed out. And it is. However, dynamically, as you'll see shortly, I can actually very easily change this. I can change the settings for the exposure, and you'll see the moon start to dim out a little bit darker. And so it gives you more detail. So the washed out areas will look better. What's that?
It looks better.
Oh, okay. So you're seeing it in less than 30 seconds, apparently. So I'll do a zoom and then tell me how long. This is getting our feet wet, folks. Just trying to get in. Okay, so if I zoom, all right, Oh, no, that's taking a picture. Okay, never mind. I accidentally took a picture because I'm working in the dark. But I'm going to change this setting. There's the zoom. I zoomed twice now.
All right. It's still not zoomed, so let me
Okay.
see how long it takes.
All right. We're timing this.
About 10 seconds.
Okay, 10 seconds. Okay, so we get a 10-second latency on all this right now. That's not bad.
No.
That's not bad at all. Not at all. Okay, cool. And so, that said, whoops. Sorry, that was me elbowing the telescope. I apologize. That's cool. So it's like Keith's probably, if he's watching this, he's going, "Hey, what the heck is that? That's why is the moon up on that screen? I don't get it." And we got other things to do too. I have a couple other places that I want to take you to here momentarily. You got to keep in mind, folks, it's not dark yet. This is still a rough daytime view. It's not actually daytime. It's just dusk, and we still have evening twilight. This is called. And evening twilight makes it impossible to view anything of import until such time as we actually have the opportunity to see something that's in the dark. You'll also notice that in a couple seconds, as I'm moving around the moon, you'll see that when I move up and the image stabilizes, it seems to drift just a little bit. Well, that drift is actually the result of the motors inside the telescope catching up. And you'll notice that it does stop, and it does get solid. And the other thing that you're going to notice is there's a little vibration. So when I stomp my foot, like I'm doing right this second, you're going to see that the image shakes a little. That is not a failure of my observatory design. It's a failure of how I ran the cords, because the electrical cords are going down the steel pier, which is 150 pounds. And they're contacting and touching the floor tiles that are doing the anti-fatigue for the feet type thing. And I have to cut around the wires so that nothing is touching the floor tiles. When I do that, I could stomp on here all day long and you'd never see anything moving. So that's where we're going to go with this. Now,
I have a question for you.
Yeah.
Can you play with the ISO and the gain on the camera to brighten up the image? And
of course, I can do that. I can actually, if I do right now, okay, you'll see that I can actually. Oops, hold on. That's what I do here. Okay, that's fine. All right, so then I could actually go quite bright with this, to the point where if I move the moon to the other side here, a little bit over to the right, like this, and I keep going, you can see there's a little glow, and that glow is the other side of the moon that's being illuminated. You can just barely see it. Now you can see it a little better. You can see the curve, that gray curve coming around from the top, where right at the very edge of the stream, you actually see the little edge of the moon that's lit, and you can see the curve of the moon a little bit as it goes down and to the left. That is actually not the dark side of the moon. It's just the unlit side that always faces us.
Right.
And that's something that is, is important to understand. Some people say, "Look, I can see the dark side of the moon." Well, actually, you're seeing the regular side of the moon you always see, but it's pointing the orbit where we don't actually see that lit up because it's too close to the sun on that side of the Earth at the moment. Remember, it goes in a circle around the Earth from above. And so as it's orbiting the Earth, the shadow on the surface of the moon seems to change to us. So when we see the moon, the way it does, like right here, all right, and so I'll bring it down to a manageable, that's beautiful. As we see the moon here, you'll see this is actually, in what's called first quarter. Now, that people look at that and say, well, it's half lit up. And that's actually true, okay? And they'd say, well, why is it a quarter if I see half of it? That's because it's 1/4 of the way around in its orbit, and that's what determines what we call the phase of the moon. So last quarter is, when it's on the other side of the Earth, and the other side is lit half, so to speak. And then at this point, at any one time, the moon is always fully half lit because from space, you just can't see the other side of the moon in this image that is lit as well. That's actually the dark side, which we call the dark side. So during our new moon, when we don't see a moon at all, that other side is actually the dark side of the moon fully lit. So it's interesting that both what we call the lit side of our moon and the dark side of the moon, so to speak, that's just a side we never see. It's never dark. It always has its own phase affected, just like we see here. The front side of the moon and the back side of the moon see the same amount of sun. And that's sort of a mental hurdle that people say, oh yeah, that's true, huh? And that's true. And that's kind of a neat little thing that you learn, as you go through school and start doing your astronomy. Now, it's getting dark enough. I want to actually take us on a journey to some of the really cool places that are...
I got a question. Before you do that, I got a question for you.
Okay.
Is it necessary when you're viewing these objects that are distant that you need the eyepiece, or can this camera simply do it itself?
Well, this is the standard view when you mount the camera without a lens, without an eyepiece, directly to the telescope. Now, this telescope is effectively a 1600 millimeter telephoto. This is the standard view. Okay. Okay.
Mm-hmm.
Now, if I do the zoom feature, where I zoom in a little bit, okay, now we get this extra power for our troubles. But this is digital zoom. This is not actual zooming using a lens, which is always a little better. So, for instance, when Paul changes out a lens or uses a Barlow lens, which is actually a lens that you put in to multiply the power without having to change the camera and without having to do a digital zoom, then it's better. What I have here is good for what we're doing. I use it actually to focus, believe it or not. So, like, for instance, when I go and I zoom in the final amount here, you'll see in a couple seconds that the moon now it's about as sharply focused as I can get it with this setup right now. I'm sure I could do critical focus to make it a little better, but right now I can't. And
Mark, are you using the digital zoom on our cameras?
yes, I am.
Oh man, this is and you're doing the C2 button, right? You're getting it in even closer than what I was doing.
Right. We can even go more than this. There's other people that actually do just a little more than this, and Keith is familiar with the technique, and he'll tell us about it when he comes on at some point, because we got to have him on. Hey, we're showing the moon, and doesn't he own the moon? I mean, they own the moon. So I'm not even paying them royalties for this, so this is a real problem. So I'm not going to stick to the moon if I don't have to, but you have to admit, it's really a beautiful satellite of the Earth, and I really like it. But, we do have to move to other things, and I'm trying to think about where I'd like to take you next, because now it's getting a little dark, and we can actually maybe do some of this stuff. That grinding noise you hear, that's the sound of the dome spinning. So that's something that we have to be careful with. Oh, I know where I'm going to take you. I am going to take you to a really cool place. I'm not even going to tell you yet. I'm going to take you actually to the star Vega, and there's a reason.
Okay.
Vega leads to a couple of very cool objects. Now, with the moon out, I got to tell you, when the moon is out, deep sky objects like faint galaxies and things like that don't look as good, but we'll try to find them. We'll try to do it. The camera has a really good way of helping us find things, and so we may do that. We may be able to find these faint objects this way. But what I'm going to do now is take us to Vega, and okay, get out of this. Okay, and I'm going to tell us to go to a star, and I'm going to say we're going to go to a star named Vega. I'm using a computerized telescope, and this telescope is really quite nice. It's a workhorse, and most people that have this telescope don't like to part with it. You know, I did sell one of my other telescopes, and I'm glad I did because I got this one as a result, and I'm telling you, this is really good. All right, let's head to Vega. You're hearing the telescope. Okay, there it is. See that? Telescope is well aligned. Vega was on the other side of the sky. All right. Now, that doesn't look like much, I grant you, but there's something else near it that I do want you to see. But I just want to play around here for a few seconds just to give an idea of what we're actually seeing. Let's go down and show you when I actually do this, and I actually zoom in a little bit, not zoom, but I use this ASA setting. I'm actually changing the exposure. Notice how I make it really bright. You'll see that in a couple seconds. And you can see the stars around it. Now, I want to tell you about Vega. All right, Vega is an interesting star because it actually is what we call a standard candle for us. By standard candle, I mean that Vega is a star of a particular type. It's a star that's called a A05. Now, what does all that mean? Well, we have a lot of stars out there, and among them, we have stars that are called type O stars, which are the hottest, the brightest, and the biggest. They tend to explode in supernovas when they finally die, and they are stars that are amazingly powerful. Then we have B stars. B stars, first of all, O stars, we see some O stars in Orion and in Orion's belt. So it's really, really, these are very, very bright stars. And they could be thousands of light years away and they still look really, really bright. So let me give you some other information here about Vega. Now, Vega is in the constellation called Lyra, which is the harp, and it's a bluish white star, and that's because of its spectral type. Its spectral type is A, all right? Well, its spectral class is A, and the spectral type is A0, meaning it's the brightest of the A stars and the most intense. So that goes from A0 to A9 for all these different types of stars. This particular star, when we look at Vega, we actually see that Vega has actually got Vega has other stars around it here, but these are just what we call field stars. They're just in the area around Vega. Now, the thing about this star is that it comes from an Arabic word that sort of means the swooping eagle, which is interesting because near Vega, this is one of the stars in what's called the summer triangle. We have the star, sorry about the noise, I've got a low-flying aircraft. We have, in the summer triangle in the night sky, we have a star called Deneb, which is in the northern cross, which is the Cygnus, the swan, and it's the bright star in there. Next to it, of course, we have Vega in Lyra. And then down in the actual eagle, which is the swooping eagle, is Altair. Okay, or if you play a particular game, which I'm sure some of you do, you recognize the name Altair. And that's, I know that because I play that game, and so does my son and my other son. But the bottom line is, this is one of the stars in the summer triangle, and you can see why. It's one of the brightest stars in the northern hemisphere, and then especially in the summer. So this is a star that is actually, it's a very interesting star because the interesting thing is, in 12,000 BC, okay, you're looking at the North Star from 12,000 BC. And You're going to say, well, how is that? Did the stars just move through the universe? No, no, no. The Earth is wobbling on its axis like a top. And part of that circle that it would circumscribe, if you could watch where the North Pole is pointing, goes right through Vega. Now, isn't that cool? You're looking at a North Star from 12,000 BC. Okay, but you also have to understand that the stars haven't moved that much relative to our time on Earth and our history. It takes them hundreds of thousands of years to visibly move. But nothing in the universe is standing still. This star is moving through the sky at a good rate of speed, and the other stars around it are moving at a good rate of speed. There are a lot of stars that are moving fast. One of them, and first of all, let me just say this. Some of the stars that are the brightest stars are not necessarily the closest to us. Some of those stars, as I told you, were the O stars, which are really, really hot and bright. B stars are next, and those are kind of blue. You know those because they're the Pleiades, the seven sisters. All the stars in the Pleiades, Alcyone, Europa, these are all the B-type stars. And then we have the A stars, like Vega here. And Vega is the leading candidate, the A0, the very first in the list for the A's. And the nice thing about Vega is that the star itself is just doing normal hydrogen to helium burning like our sun. It's just got more hydrogen, it's just got more mass, it's just bigger in general, it's more luminous, and that's a trait we give stars too, something called luminosity. And this star has a fairly high luminosity. So we see that Vega, has a lot of characteristics, and it's also another interesting thing about Vega is it rotates very fast. Our sun rotates too, It goes around. That's why sometimes you see sunspots coming in from the limb, the edge of the sun. They rotate over the center, and then they lazily go around, around the star. Vega, actually can rotate once around in 12 and a half hours. It takes our sun many days to rotate. So Vega's a very fast rotating star as well, which is kind of a cool thing. And I really like that. So this is Vega. Now, interesting, next to Vega, we're going to take a jump down, all right? And we're going to...
Now wait, before you move this,
yeah.
The Sony A7S is showing it in its true natural color, correct?
That's correct. But you know what? If you listen, and guys... Bill is really hyped on the A7S because he had a success with it earlier today, so pardon him for his over-exuberance. But let me say this. And that's fine, Bill. But let me say this. The stars will look all white if you have the wrong settings for the ISO, that is the sensitivity. If you set it wrong, then it's going to have a white look to it. So we don't want a white look. We want to have the actual color. So for that, I would actually have to change it down. Now, Vega, it just turns out, is white. It's almost white.
Mark, I don't mean to interrupt you, but you had a streak, like a reddish streak, go across your screen. Is that a shooting star?
It might have been, because right now we're actually on a 30-second exposure here. So we're as low as we can go at this ASA, which is currently 100. So let me change the ASA and go up to, say, 6400, and let's see what we can get here. All right, well, I'm looking at it, and I don't see a whole lot changing.
You have to go back to your video and check it out at some point.
I will. All right. So right now, I think where we are is we're gonna move forward here, and I will. There's a couple things with the camera too that I want to figure out moving forward as well. So there'll be another thing, but I do want to take you to another place. This is actually a fascinating star. So I'm gonna let you watch the screen go by. I'm gonna have you. See it.
Another question. Another thing.
Yeah.
Did you start SNAS up? Because this is where we have a clock on the screen.
Yeah, actually, SNAS was started, so it must have stopped. But that's okay. Don't have a clock. No, okay, that's an oversight for this one. It is there. It does work.
Oh, that looks excellent.
Okay.
Oh, God, that looks great when you magnify. That is incredible.
Yeah, that's actually just trying to show you how, and I want to tell you something else. When you look at this, this is Vega, and it's in its actual appearance. Now, you see how it looks like when you see those spikes. I know it went back. It'll come back to full zoom again.
That one, I love that the way that looks.
Around the edge of it, not in the center, but around the edges, you can actually see that there's a little bit of a blue tinge.
Yes.
Yeah, and that's important because that blue tinge has something to do with the color of the star. All right. Here's another way. I'm going to give you another way that you can tell the color of a star, and you'll laugh at me for this, I think, but I'm going to do it right now. All right, and you'll see this in a couple seconds. All right. Now, no, this is not a space donut that you're seeing when this comes up. Okay, that is a defocused star. I took the focus down. By doing that, you can see the actual color of the star more clearly. And there's something else you can see. You can see the turbulent air moving past it.
Yeah.
Isn't that interesting? And that's something that helps you determine how good the seeing is and the transparency. Those are two astronomers' important settings. All right, and I'm actually moving up a bit now and actually making it larger. And I get, because I'm the chief photo and video analyst for the Mutual UFO Network, I get a lot of these from people who said, look what I photographed. It doesn't move. It's flickering like crazy. It's intelligent life. But unfortunately, what they're actually seeing is a defocused image of a star, or they didn't get it focused right, or whatever. I'm just focusing by hand right now. I mean, I have an electronic way to do this, but you'll see now that I'm just going to go back and forth. There we go. All right, so now, so that gives you the idea, and you can actually see that the color of Vega was really blue, and that was important. I wanted you to see that. Now, if I'm going to take you to another place now, so enjoy the screen as it moves. All right, and I'll take you. We're going to go slowly. I'm going to go a little faster than that.
By the way, they said something about a double cluster, if it's possible.
I realize that. Yeah, the double cluster is a little bit low right now, and I've already thought of that. It's on the observing list. Okay, now I'm moving to another area in the sky. All right, and that's not it. Here it comes. Okay, ready? Let me see here. Oh, hang on. Check that out. Okay, this is a double star. Those two stars, these are called Epsilon Lyrae. And
yeah, I know that is, yes.
Okay, but I'm talking to everybody else, Bill. They don't know. So, Epsilon Lyrae is a star in this constellation where the star actually is composed of more than one star. Okay, and the Greek letter epsilon, stars are given the letter alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, xi, omicron, pi, rho, sigma, tau, upsilon, phi, keep, psi, omega. That is from memory. I am not reading a thing. It's dark in here. Okay, that's what happens when astronomers do their astronomy thing. Okay, we just learn crazy stuff, and that's one of them, the Greek alphabet. Now, as you can imagine, the brightest star in the constellation is given the Alpha moniker, the name. So therefore, what is Vega? Right, it's Alpha Lyrae. Okay, this is Epsilon Lyrae. Now, in the early times, this was thought to be one star. But they could see, when you look at it, you can see that it's not. It's actually two. And Epsilon Lyrae, these stars actually are orbiting each other. And it takes a long time for these stars to orbit each other. But there's something else about this entire assemblage of stars that is even more fascinating. And that, and I will show you, and I just have to figure out the best way to show you. I mean, I think I can do it. That's this. Okay, when you look at these, you see these two stars. Mm-hmm. Let me try to zoom in just a little. See if we can get something else in there too. Let me just change this a little bit. Now zoom a little bit. I'm not sure we're gonna get it, but we're gonna try. All right. Okay. Hard to see, but let me try it with the camera. I'm going to adjust with the camera. I'll come back out for a second. I'm going to adjust the settings in the camera, and I'm going to make these very sharp pinpoints, okay? And now I'm going to go back in. Let's see what we got. You can almost see it. Let me see it again. All right. Let it stop here.
That looks pretty pinpointed, yes. You got it.
Yeah, except that I'm trying to show you that this double star is actually a double-double. Each of those stars are also binary stars. They have companions going around them, and you can see those. And this is, again, because it's a rather, not a still night, because it's not a very still night, unfortunately you can't really see it that well, but it's immensely, it's an immensely beautiful object when you see these two sets of doubles. You can actually see that the bottom star is actually elongated a little bit. And I'm going to try some manual focus to see if I can get this even closer. I got to take it out of focus a little bit and then bring it back in focus a little bit. So bear with me a sec. Let's see what we can do. That's about the best we can do on a night like tonight. In fact, it's not really high in the sky yet. When it's overhead, wow, you'll actually see it very, very brightly. So this is a double-double. Okay, that's the double star we saw a few seconds ago when I showed it to you before. But it's actually a double-double. It actually has another pair each. You know, so you zoom in on the bottom one, there's two stars there, and you zoom in on the top one, it's got two stars there. And I just think that's just a beautiful, beautiful thing. So,
that is incredible.
What's that?
That's incredible.
Yeah, no, it's a beautiful thing. And now let me just try. I'm going to come down just a little more. What's my ASA here? I'm way up high. I'm going to try and bring the ASA down. I know that you won't see it here for a second, but I'm going to try this and see if I can actually find that. I want to find that double-double. I want to see if I can see it. May not, but I'm going to try.
That's why our camera. I really do.
What'd you say?
I love our camera for this because you can play with the ISO. You can. That's what makes it great.
Yeah, no, that's true. Okay, you know what? You can actually see the bottom one is not just one star. This is about the best I can do with it being so low on the horizon right now. It's got to get up higher before it'll look better, and when it gets up higher, it'll look phenomenal as well. So, but this is cool. This is exactly the kind of thing that I think is great, you know. And I'm sure as we move forward, and again, as we start to look at other objects, it'll be pretty cool. Now, I'm going to try another object that we're going to look at, and let's see if I can find it. Let's see if the telescope will find it. All right, this is not an object like a star. This is something different. And I told you that deep sky objects, that is galaxies and things, are not very visible. When we have a problem like we have tonight, where we have a moon that's fairly bright. But I'm giving it a shot anyway, just to see what we get. And you won't see anything yet. You got to give me a minute here to try and figure this out. See if I can do this. Of course, the telescope changes orientation. It makes it like impossible to figure out what's going on here. Let's see here. All right, let's try. I'm going to change to a higher. Get out there. How are we doing? What do we got? Okay, let's see. All right, so I'm bringing the ISO up. That's the sensitivity, and that's pretty cool. I see what we're looking at. I'm not looking at the object yet, but we'll get there. And let's see here. Welcome to astronomy, folks.
It's incredible, though. Yeah, you could almost see the double star on that last image when you had the.
Yeah,
You can almost do that.
It's hard. It's difficult because unfortunately, we have the issue of the bright moon, so we're not able to see it like we would expect to. I'm hunting around for this thing so I can see if I can find it. Yes, you're hunting with me, folks. You're going with me at the same time. Now, when in doubt, one of the things you can do is you can actually take an exposure. So I'm going to try taking an exposure. And I should be able to do that. Just a sec. I'm going to cut this off here and try taking an exposure. So right now, what I'm doing is you'll see that I'm taking a little bit of an exposure, and when I do that, it'll flash the image on the screen for a brief second or so, and you'll get to see what I'm seeing, native for a couple of seconds, and then it goes away. But what that actually looks like, to make it not go so fast, is it looks like this. So you can see it, and then you'll see it in a couple of seconds. And then I did another one which is not quite as dim, or not quite as bright. So this is the photo right there. Now the object I'm looking for is not there, and there's a lot of bright moonlight right now. So I'm going to try and find it a different way. I know I'm not telling you what it is, and that's on purpose. Just trying to keep the interest there for a minute. Okay. Still looking, hang on. Alright, what do we got there? Alright, let's take I'm going to do a 3.2 second exposure. And the nice thing is, you get to see what the result is like right away. So now it's taking exposure. That's when the screen goes black. Then it counts for 3.2 seconds, and then it comes back. And this is what we saw. I don't have it there yet. The moon is killing us. So I will keep trying. And let's see. I'm going to take another look at something else, because I forgot about something in Lyra that I wanted you to see. So we're going to go back there for a second, actually, and I'll try to find something else. This next object you're going to see. This next object you're going to see is something that's the remnant of a former normally burning star. It's a dying star, and you're going to see this for yourself in just a second as I bring it in. Welcome to the observatory. All right, let's see here. Let me bring it in. One second. One second. A minute.
And if anybody wants to ask Mark questions in chat, I will pass them along. So post those questions.
Yeah, but you don't really ask me. I mean, that would hurt. That's a joke. Alright, let me go. Yeah, Mr. Moon, hey, it's just like no fun. Okay, let's try this. Alright, we should be right. It should be right about here. Right about here, oops, or maybe here. I'm hearing weird vibrations in here. I don't know what that is. Maybe it's maybe it's mice. I'm not sure. Just kidding. Let me take a quick exposure. Oh, there it is. See, that it was in there and I couldn't. Here, I'll show it to you. Okay. If you look just near the top of the image, what do you see? Okay, when it comes in. Do you see that?
Yes.
Okay, that's called the Ring Nebula. That's actually a former star that has since lost its atmosphere to space, and I'm gonna bring it in better to see here in a sec. Okay, there it's centered now. And now what we're going to do is I'm going to change the ASA sensitivity and the speed, and I'm going to make it so that the ASA is a little less sensitive, and we're going to try and take an image of it at 32,000 ASA for 2.5 seconds. So here we go. The screen goes black while it's taking a picture, and then it comes back. And now you can actually see the Ring Nebula. Alright, and you'll notice that the stars are not dragged out and trailed. That's because we actually have a very good telescope, and it's tracking the stars very accurately. The other thing I noticed was in this last shot, the dome was just a little bit in the way, so I'm going to do one more shot. And then it'll be done.
You know something? I'm gonna have to start taking more photos of astrophotography. Now that you're doing this, I definitely got to do more of that.
Oh, and there's more to come. So now look at this. See, this is the Ring Nebula. Now this, I'll zoom in here. I think I can actually zoom in here, like this. So I know that it's a little rough right now, and we're gonna try and refine this. But you see that shape? Let's talk about that. That round shape, that Ring Nebula, is actually the sloughed off outer material from a former star. And that star is a tiny little pinpoint inside of this object, inside this, that you can't quite see it. But I'm going to actually try and refine it so that you can. And that means, yeah?
So are those the gases expanding from that star?
Those are the gases that are the leftover remnant of the star's atmosphere that are expanding, yes. And now what I'm going to do is I'm going to make this a 4-second exposure. So, and I have it, so you'll see it go dark, and it's going to go dark for 4 seconds.
Okay.
And this is while we're taking the picture.
Tron wants to know what type of telescope you have.
I'm using a Meade Systems telescope that has a GPS built in, and it's a 10-inch system, so it's actually pretty cool. It's called an LX200 GPS. And okay, we're done with the exposure. Let's go take a look. All right, so this is actually a little better. You can see that it's got a little bit more detail, and you'll see that the star images are just a little bit soft because the focus isn't quite there, and we have to work on the focus a little bit here. But if you notice, okay, you see how it's red on the outside, it's kind of bluish green in the middle?
Yes.
Those are the actual colors. So when you see, that doesn't mean the star was bluish green or anything. It just means that this is how the outer gases appear, because they were illuminated by the still hot central core of this.
Okay. I have a question for you. Determining the color, can you tell what type of gases they are specifically by the color?
The color will help, but the thing is, we can actually get a spectrum of these stars and these envelopes. These are called envelopes, these gas envelopes. We can get a spectrum of these things, and we can break those colors out, and then we'll see lines in there that tell us a specific chemical signature for the element that we're seeing. In this, we're going to probably see oxygen, we're going to see hydrogen, may see some helium, and they're all mixed together. And so you have to be a sleuth to take them apart. I did a lot of that when I was getting my degree in astronomy, taking nebulas like this and getting a slice through the nebula with a spectrum, and then trying to figure it out. Now, I'm going to go and do a little bit longer exposure, and I'll tell you why. I would like to be able to show you, if I can I'd like to be able to get that central star. So I'm going to do a 6-second exposure at a slightly higher 16,000 ASA. So
I have one more question for you.
Okay.
This is awesome. I mean, I know everybody else is enjoying it in chat as well.
Well, I mean, as long as you don't think it's just a clumsy effort to show them something cool, I'm thinking it's very it'll be a very educational thing. But I need their feedback.
Based on the distance of this star, how long ago are we looking into the past? In other words, when did this first start happening to this star that we're seeing this now?
Well, that's a good question as to like how long ago it happened. But we can make a guess, and that's I think the thing that we can do here. But before I do that, I just want to tell you, if you notice, if we look at the star now, what I just took a picture of, you can actually see that central star, can't you?
Yeah.
Yeah.
Yes.
That central star is very faint. It's like a between 11 and 14 magnitude star, and that's very it's sort of faint. Now, the Hubble imagery of this is of course astonishing, but this is a backyard, in this case front yard, observatory that's a reasonable aperture telescope, and what we do is, and as I took many pictures of this, and then what I do inside digitally is I stack them together and align them all up, and then I compensate for the extra noise that's been introduced, because that's actually, by stacking them together, you keep the signal and you throw away the noise. Now, what signal? The signal is like the blue part, the orange part, the yellow part, the white of the stars. That's signal. Noise is the background, discoloration that you can see on the screen. That's the camera. Those are the camera artifacts. They vary from picture to picture, but you get rid of those in the process, and it ends up making a beautiful imagery. I took a picture of this, the Ring Nebula, and you saw it online. If you did look in my Facebook site, you actually saw it. And the neat thing is, if we talk about this, this object we're looking at is 1,400 light years away, to answer your other question. And that means that if you do an angular diameter, that distance of that cloud, that residue, the leftover sloughed off outer layers of the star, is going out several light years already. So if you were at that star, you might not even see this. Now, the reason I say that is because we see it in a photograph, but look, if you just looked at it regularly, this is seeing it with your eye. Do you see it in the middle there when you get to it? When it comes up, just look. Yep. And this is with assistance from the ASA and the other factors here. We're actually we're actually showing it,
It's amazing.
With some adaptation. So now we're actually seeing it like that. Now, that is absolutely astonishing to me.
It is. It's amazing.
Yeah, I think it is. And now, what happened was this star was a normal burning star, and as it got older, it used up its hydrogen gas, because hydrogen is used in a star to form, it's compressed and forms helium. That's called the nucleosynthesis, or the proton-proton chain, if you want to be technical. And then when that is used up and that hydrogen is all gone, well then the star begins to contract, because there's not enough outward pressure of radiation pressure from this hydrogen to helium process going on. And what that does is that causes the star to contract, get brighter, because as it gets smaller it gets brighter, and then it gets hotter again in the core. It gets hot enough at that point to start burning helium into things like carbon, nitrogen, and oxygen, and when it does that, the star begins to blow again. Now, this is how red giants are made.
Right.
And the star bloats up, and it expands massively. Like if our sun were to use up all of its hydrogen,
I'm just going to ask you that.
I knew you were. Okay. If our sun was to use all of its hydrogen, I'll go back to this cool picture. Then what we would find is that it would end up making a similar object in the sky eventually, but it would first blow into a red giant star, right? That would eat up Mercury's orbit, Venus's orbit, and the Earth's orbit, and that's it. There are stars out there that will go out all the way to Mars just normally, because that's how big they are. That's a massive star. It's unfathomable. People can't comprehend
A star that large.
No, they just can't. They just can't. So, this is called the Ring Nebula, and it has a designation of Messier 57, M57. Charles Messier in the 1700s, he came up with a catalog of objects that could be mistaken for comets, because he was a big-time comet hunter. And these objects like this, he didn't think of them as, oh, that's a dead star or a dying star. No, he thought of them as an irritation, things you wanted to avoid. And he unwittingly created this catalog, 100 and some odd objects, that are all stuff that astronomers everywhere just want to go check out and just love to see. And this is why we have the Messier catalog to this day. And this gives us some really neat insight into the minds of the people back then. They didn't care about these things because they couldn't figure out what they were anyway.
Now, that brings up an interesting point that he says, with this kind of star that is in this phase, flicker.
Well, the star that you're seeing in the center there, that little tiny dot, you're seeing a white dwarf. That's a white dwarf star in the middle there. Okay, and this camera and this telescope can see that, and that's what's good. The combination's good to see that. All right, I mean, this that star in the center doesn't really flicker anymore. However, it's hot enough that its radiation that it puts out causes the gases in that expanded cloud, even multiple light years away, to absorb some of that energy and then spontaneously give it off. That's what atoms do. They take in energy and then they want to relax and go back to their original energy state. Well, that's what we're seeing here, and we're seeing this thing actually. The color that it's showing us is indicative of the gases, which is what we talked about before, and then we would see in its spectrum confirmation of what they are, and we would know it.
This raises something that somebody else brought up. Using different type of filtration systems, like looking for infrared, or like you said, this one would be giving off some type of radiation. Yep. Are there different types of filters you can use to spot these objects in the sky?
Yes, as a matter of fact, in an area where your sky doesn't look very dark because you have light pollution. Light pollution is usually what type of lamp? Sodium vapor lamps or mercury vapor lamps. Mercury vapor lamps, I have mercury tubes here, gas tubes, and I can show you the spectrum specifically of these bright line spectrums that enter up into the atmosphere, get scattered around and come back to your eye and obscure these beautiful telescopic sights that we're trying to see. And then the other one is sodium vapor lamps, and we have high, low pressure sodium vapor lamps, and those are a yellow coloration. So these things are a problem. So they have what are called sky glow filters. These are filters that you can use to actually get rid of that glow while you're looking at something in the sky. And then if you take a picture, you'll say, "Oh wow, that's a beautiful picture," So it's pretty cool, and so you can actually get the best bang for your buck that way. I'm not using any filters, and I have a reason for that. I want to be able to judge the darkness of the sky that I'm in by the raw photos we see, like we see here. This is a raw photo. If you notice, the background is kind of a never mind the speckly colors that you see all throughout the picture. That's actually a product of the high sensitivity that we have it set on. But if you actually look at with the camera, if you actually look at the color that you see, like normally, like this, like where it's just sitting here, it's coming in a second. I'm just looking at the sky now. All right. Well, this color that you see is actually based and caused by the brightness of the moon in the sky. All right. Here I do have some sky glow near the horizon, but in general it's not a bad location. You know, you can see the ring nebula pretty easily, like right there. You know, it's difficult there, but you know, you can actually see it. You know.
Now, you've mentioned to us, to a few of us, that you're looking to move to a darker location. Is that going to change the imagery that you get, say, of this nebula when you're in a darker sky location?
Yes. When I get this down to Arizona, what we're going to see is it'll be a very different setup down there. I'll be able to take this very same setup that we have here. We'll be able to show us some superior performance. Because, you know, the skies are clearer and darker, and there's more stars per unit of sky glow. Okay, around here there's more sky glow per unit of stars. That's anywhere in the Northeast, not necessarily just here, but it's anywhere in the Northeast. So, and I have maps, dark sky maps, and these dark sky maps show where the darkest areas are in the whole country. And this area here is reasonable in some areas and not reasonable in some others. So sadly, that's unfortunate, and I don't like it, but it's what it is. Now,
it is light pollution, so to speak, correct?
It is light pollution. Yeah, that's correct. So I'm not happy about it, but it's the best we got right now. And I know that some folks were looking for the double cluster, and I think that it's low. Unfortunately, I gotta see if we can actually pick it up. Some of this is subject to your own horizon. The horizon that you're subject to, where you can't always see. You can't always see what you want to see. But let me just look it up and see if it's nearby enough that we can actually look at it. I know that it's beautiful, and it's just gorgeous. And you're not gonna end tonight without seeing a beautiful cluster of some kind. And there's plenty of them out there. But I'm gonna do that. We're gonna certainly find it. But first, I want to find one more thing, if we can do it. I'm going to look for one other object that I want you to see, if I can show it to you. Again, it's not as easy when you don't have when you have a moon out, but we're going to try it anyway. I know I popped. What?
Dave Shock is passing a message to you that M13.
Oh yeah, no, that's on the list. That's definitely on my list. And that's nice and high. We're going to check that out too. Absolutely. Right now, you'll see the stars streaking by here as the telescope is zipping around here. Oh yeah, let's see if we can find this.
Here's another question from Charles Smart.
Yeah.
He wants to know, what is the altitude at the Arizona site? How much does altitude matter?
Altitude plays a tremendous role. If we can actually get, if we can get something that's, if we can do altitude that's fairly high, then we're getting above a lot of the ground garbage and stuff, and that helps us, because a lot of it is difficult to have to deal with, and the altitude is important. I'm craning my neck just so you know. The altitude is very important, because when you actually look at an object when the altitude is actually high, then you find that the objects will tend to actually look darker, have higher contrast against the background. All very, very important stuff, I'm just doing some test photos here to gauge the sky. What's interesting is every one of these stars in there that we're seeing, every single one of them has a name. They're all cataloged. They're all they're all basically known and are very obviously in a catalog of one kind or another. And so the bright ones are in certain catalogs, and the faint ones are in like other fainter catalogs, like faint star catalogs. Faint star catalogs like something called the Hipparchus catalog or the Tycho catalog, stuff like that. And I think that if we look at, oh yeah, see, I'm kind of too close to the moon here to look at this particular thing, but I'm going to try anyway, because I would like to give you the option of seeing it, if we can get it. Yeah, it's not going to be easy tonight. Alright, when it's moonlit, it's very hard. Again, yeah. I said we weren't going to go for deep sky objects, and then I turn around and try and do deep sky objects. And that's me being impatient. So I apologize to you guys. And I do want you to see a few things actually that are very interesting. And I'm going to do that here in just a minute. So now I'm going to go for, let me look here. I don't want that. I'm looking through my list, guys, just so you know. Now, this telescope's also, this is also capable of tracking satellites. So I can actually turn this telescope to a satellite if there was a point where we knew there was a satellite that was going to go by. I could actually, set up and get the what are called the orbital elements of that satellite. And orbital elements are are very important because they give you all the exact parameters of an object's orbit, and that's something that will be able to allow you to go to it in the sky and just see everything it's doing, and follow it. It's also a good thing when you have orbital elements because they get updated from time to time, and I think it's very important to make sure you update your orbital elements. So now I'm also waiting for Cygnus to come up out of the haze. So I'm trying to find one other thing that I think you may like. Right. Just a sec. And that's what happens. You kind of gotta you gotta bear with me as I do this stuff.
No, do what you gotta do. I'm actually. Somebody wanted to know this is just a specific question. What is the price range for a telescope like this, Mark?
See, that made me cough. This telescope, we're looking at about a total of about $8,000 with everything on it.
Wow.
So you're gonna run out and buy one, Dell, or your mom will kill you?
Not me. Somebody in chat. Not me.
Oh no, I think you were just saying that. I think it's
you know which one I want. Well, we won't get into that, but
yeah,
the one that break down and take on some mobile sky watches.
Yeah, but that's the one that I was advising you on, right?
Yeah.
Now, folks, you got to understand. Bill is trying to get a telescope that he can use for a mobile sky watch. That means doing what I'm doing now, but live in the field with people standing around and looking at the camera with him. That kind of thing is a cool option, but unfortunately, he was sort of hard up for the cash to actually do it, and I understand that. That's just unfortunate.
Yeah, I mean, in time, right now I'm working on the projector, which I got the screen. There's going to be other interesting things, and believe it or not, Mark, like you said, I am so excited that I put that Sony A7S on the telescope because it was like amazing. I haven't done it yet, and when you told me about this, it's incredible. It's incredible what it can do.
Yeah, you were just setting it out there with a lens and looking in the sky. Wow, But you didn't get to see the real value, and the real value is what you see when you actually put it on a telescope. So hang on, folks. I'm bear with me here. I gotta take a drink of Snapple. Yeah, that's better. So I don't know. Let me know if you guys think this is valuable. If this is good. I'd like to get some feedback from you. We're moving at the speed that astronomers move at. Again, this is the first night. So it's a little bit slow, a little slower than I'd like it to be. But I will make sure that I step up my game to make sure that we do it right, because I have every single desire to make that happen. Okay, let's go here. All right. I'm just looking for something. Hold on. Oh, wait a minute. Oh, great. I had a sky view thing in my hands here, and I had set it to look for like 9 o'clock.
Mm-hmm.
And I realized, wait a minute, I know that's already risen. We already kind of looked at it, this thing. And then then I realized, oh, well, duh. I had frozen it in time, like an idiot. So no wonder we didn't see it. Yeah, double cluster is actually, it never sets, but it's low right now. And because it's low, that's not helping us. Yeah, alright. Just looking at a couple things.
Yeah, because the screen is still on the same set of stars.
I know it is. And I'm trying to move them to something else that's a little better right now. And I will do that. Well, you know what? I'm gonna go to something else right here. The double cluster is not a good target right now. I want it to be, but it's not. It's no fun. It's not playing with us, and that stinks.
Is it the moonlight, or?
Yeah, no, the moonlight's fine. In fact, clusters are the right thing to look at when it's this, when it's got the moonlight, like this. So let me do this. This I know like that. I want to do something here. Yeah, that's still set. Oh, I think it is. Hold on. Where is that?
Right. Everybody's enjoying this on your channel. You got 44 viewers currently.
All right. Well, I appreciate that people are sticking around and not saying, that guy is crazy. Because I know I am, and that's okay with me. I know I am, and I accept that.
It's good, Mark. It's crazy good.
Let me, okay, you may not see anything right here as we move this way, but, well, the axis still, how about that? I'm turning this around and the telescope's actually, that's funny. Let me go, it's actually still in view. Okay, let me try something here. Okay, now I'm going to go to this next thing, because I'm going to try it and see what we get. Which I will tell you. There it is. Just a minute here. I'm now going to change my ISO to something a little higher. I'm going to change the sensitivity a little higher now and set the time, the exposure time a little bit differently. We're kind of down in the murk right now, so I apologize for that. But I'm going to try to show you something that I think you will like.
Now, I got again. This is a question I asked you earlier. Will putting when you're able to put the 1.25 eyepieces, is that going to make a dramatic difference in what we're viewing right now through your telescope?
Not really. It won't, but it will make a difference, but not a huge difference. What the heck is going on there? Okay, here we go. Alright, now let me do this, and then this, and then this. Oh, God, that's Saturn. It's in the murk. I don't know if you can see that.
It's quite small, but
Yeah, it's murky with it's down in the murk. Okay. So you can see it's low here. It's low. So it's actually not that good. I'm going to try the micro focuser. That's a little better. So you can see that there's, and this is actually instructional. If you notice, you see, let me change the speed of this here. You can see that Saturn looks okay sometimes, and other times it's a little weird looking. It gets all shimmery. Well, again, if I were to defocus this, you would actually see how much air is turbulent between this telescope and Saturn. All right, but the fact that we're actually seeing it at all on a night like tonight is cool. Because it's low in the sky.
Wow.
Oh, what the heck?
That's good, Mark. That actually looks really good.
Yeah, I'm actually, hang on, I gotta open the door here because I've actually got...
You can see the rings clearly.
You're not gonna believe this, guys. Now I realize why the seeing is so bad. We're being taken over by freaking clouds.
No.
Yeah. I can't believe it. Yeah, but
I'm gonna throw this out to you, and I know I'm gonna get slammed for it. But Kerry asked this question: Is Planet 9 what Pluto is being called now, or do you have any kind of theories about all this Planet 9 discussion that people talk about?
Well, yeah, Planet 9 is actually a Kuiper belt object. That is something out past Neptune. It's formerly known as a trans-Neptunian object. It's still a trans-Neptunian object, meaning it's past Neptune. But Pluto was small and never really set well with astronomers and scientists who were trying to, decide for themselves if in fact Pluto was a planet or a dwarf planet. The concept of a dwarf planet is the thing that we call asteroids. Pluto's not an asteroid. Pluto has a very complicated surface of solid nitrogen. I'm going to take a couple photos here of Saturn before we lose. So I know that it looks kind of bad there, but I'm going to try and do one thing here. Okay, that's not very good, so what I'm going to do is I'm going to work on doing eyepiece projection stuff. I was so totally blown away by the fact that I've got clouds coming in. They're already over the dome, and they're rapidly... you know what it is? Mother Nature said, he's streaming! Quick!
I'm going to go look at the radar.
Yeah, they're I could actually put the lens back on the camera and just show you what it looks like in the dome and outside. Because we're going to be rapidly losing our ability. No wonder I couldn't see anything. I had all these high clouds that were pulling through us here. But before I do that, I want to actually try something. I want to kind of give you an inkling of what's to come. I'm going to set up the speed here of this, and I'm going to go to, before the clouds kill it, I'm going to get us to a place where I can show you something really cool. Alright, right now you're just looking at the dome. I don't have anything going on there, but I'm gonna let's do this. I'm gonna take this now, and I'm going to go even higher than that. I'm gonna go faster speed. You'll see what I'm talking about in a second. Okay, I still get the same one. Okay, I'll do it again.
I don't think clouds might be an issue for long, though, because on the radar it doesn't look like it's...
Yeah, but we know that radar just somehow just doesn't... Alright. Okay, this... I'm just actually... I'm in an area of the constellation Cygnus, which is where our Milky Way is. The center of our galaxy is not there, but we have the Milky Way running through Cygnus. So I want to give you an idea of what it looks like, just star-wise. Now, it's a bad night now, but I still want to try and show you a little bit. Now, that was a 2-second exposure. Okay, so that's actually looking toward part of the complex in Cygnus that's fairly bright, but I still want to see if I can find before these clouds kill us. I'm doing this by hand now, sorry. Alright, let's go here, go there. Right. Okay, that star right there is Deneb, which is the brightest star in Cygnus. That was the one I told you was part of the summer triangle with Vega and then Altair or Altair. And Deneb, I will now take a time exposure here just so you can see a 2-second shot. Okay, so you can see then that Deneb itself also has a lot of stars around it, and honestly, to really see them, to see more of them, what I will do is I'm going to come down to ASA 40,000. I'm going to go up to I'm going to go with 6 seconds. It's probably the last photo I can take of any amount of time because the clouds are just like racing in. But we're waiting now for the camera to take the picture. And I hope you like the fact that we're doing these dynamic photos, because I like to be able to take these pictures and show you right away exactly what happened. Here it is, that's exactly what happened. And right there, okay, you can see that there's a lot of stars around Deneb, which of course is a bright, and you can see it's a bluish star. Now, there is one star that I want to actually show you again. Hopefully we can get it. I don't want there to be anything getting in the way. Let me see if I can grab this star for us without the stinking garbage clouds in the way here.
Tony Games wants to know, can one observe red stars?
I'm glad they asked because I was just about to show you one. This is actually a red star. Do you see the color?
Yeah, I did.
Yeah, but you won't see it until I do what? You know what I gotta do now?
What's that?
You know, because I did it before. How do I show you the color of the star?
Oh, when you came out from it, when you the exposure.
No, not that. Ask that. Does anyone in chat know what I did? Remember what I did to actually show you the color of the star? When I showed it to you originally, I showed you Vega's color this way. What did I do? Do you remember?
What did it? That exposure where it looked like a disc, like a CD.
Like a what?
You came out from it. You exposed. You came out from it where you had that ring on the screen which showed the color inside that ring.
Right. And what did I do? That was a question for chat, not for Bill.
Okay, I'm not saying anything.
No, it's okay. I'll show you. I'll do it. I changed the focus. And there. See that? See what we got now? Of course, we got a little cloud passing in front of it right now. And that kind of stinks. But,
there you go.
See how it looks? It's orange.
Yeah.
Yeah. So that's actually, how you can see the colors of the stars. Really, really nice that way. Now I'll go back to focus. Because when you put it into sharp focus, all the light from that star that you want to see in color is going to one spot on the mirror. That causes issues. It doesn't allow you to. It doesn't allow you to actually see. It doesn't allow you to actually see. All the color too well. And I'm gonna just go up to a little higher speed here. I'm gonna move because I'm gonna get this other star. Something for you. This is for you guys. I want to show you this. Just a minute. Come on. Clouds move. I get mad. I want these clouds to move. That's not. Darn it. I know you can see something on the screen there, but it's not what I'm trying to show you. I'll get there. You know, I gotta let it literally hop around a little bit. Gotta literally hop around. You know, nothing like ruining a good night with, there it is. Nothing like ruining a good night with clouds, right? Okay, now, it's coming, you'll see it in a couple seconds. Alright. There it is. Now, see that?
Yeah.
Okay, that star,
yeah.
That's a double star, that's another double star, that's called Albireo. And that's actually in Cygnus. And this star, and let's just take a picture of it while we're here, because we like to get pictures. And I'm not going to do 6 seconds. I'll do 3.2 seconds at ASA 40,000, and we'll just see what it shows us. Isn't that beautiful? Okay. Now, if we go back to that and just look at it for a second. Okay. Let's zoom in for a bit. See what we can see. Okay. Notice that the colors are pretty obvious. What color is the main bright star in this pair at Albireo? Okay, it's orange. Okay,
orangey, yeah, has a orangey tinge.
And the other one has a sort of a bluey.
A bluish, yes, bluish white.
This is a very odd binary star. It's called Albireo, as I said, and Albireo is a interesting. It's an interesting star because it looks like a star that's actually one star until you actually zoom in on it. And once you zoom in on it, you see that it's actually these two stars. Now, there's another thing around this star that we don't see at the moment. In fact, I don't see anything because I actually had the dome a little bit in the way, so I'm going to take another picture just for fun. Another thing that's here behind Albireo is this Cygnus star cloud, and with a wide-angle view at a nice location, we can actually see the Cygnus star cloud very easily. And we're getting just a little bit there. Okay, that's good. And you'll see that it's going to get dimmer a little bit. But before it does that, let's defocus these. I want you to see the colors. Now you see that? See the colors? Okay, those colors are very characteristic. Notice now you can clearly see the colors. You have the orange one and the sort of the blue one, right?
Yes. Yes.
This is how you see star colors. You actually take and defocus your image a little bit, just enough, so that you can actually see the star. And I did this with professionally with big telescopes. I did this, as a matter of fact, to find what we had to find our goal star. To find the right colors. So Albireo's is neat because it's really what we call a celestial gem, and I guess you can say that the colors are indigo and they're gold. Okay, and indigo is like a bluey kind of purpley, and it's really part of this Northern Cross, and it's the end of the Northern Cross. It's actually the head of the Swan, of Cygnus the Swan. Let me bring it down a little more. Oops, that was a little more, wasn't it? A little more the wrong way. It was. Let me just drop it back. Okay, sorry about that. I had my speed set way too high. Oops, that's the focus. I don't need that. All right. So, if we're looking here at Albireo again, here's something interesting. Most stars are double stars. Most stars are double stars, and or more. So for a star to be just a singular star like our sun is sort of rare, but most stars are actually doubles, and Albireo is the same way. It's really kind of interesting. Now, the thing about it is that bright orange one is also a double star. So this is actually like a triple star system so far. And that was discovered way back in like 1976. Right? They found that it was actually a triple star system, but it looks like a double, and it's because it's that orange one has another component around it, and they're separated by 40 astronomical units, like 40 times the distance from Earth to the Sun. So 40 times 93 million miles, which is an astronomical unit, 93 million miles. So we see this, and we can't see that other component very well, but it takes about 100 years, all right, for those components to go around each other, even at this distance. Okay, so it's really kind of cool. They actually discovered the pair through a special process called interferometry, and it's a process that actually helped and has been a mainstay in astronomy for a long time. I'm going to pop out here for 1 second. Just want to change the ASA down a bit to kind of give it a little more of a darker field, and I'll pop back in so you can see it. See, the nice thing is with stars, you don't have to worry so much about doing this this magnification thing, but it helps to see the colors better when you have more surface area on the screen covered by the star. Especially when you set the settings as I have, so you can actually see the star colors. I could easily make these so bright that you wouldn't even know what's going on, but I'm not going to do that. Now, the difference, the distance to this double star that we're looking at, all right, is 430 light years. That's how far away it is. Okay, now, in contrast, the distance to the nearest star here at Earth, besides the Sun, is 10 times smaller. It's 4.3 light years. So, 10 times farther than that, and you get to Albireo here.
Wow.
Just amazing, And I think that the most interesting element of this, besides the color, is the fact that the main star, the orange one, is actually a double star itself. All right? So you have this complex motion where you have stars going around stars, and then they have stars going around those. However, that shouldn't be such a surprise to anybody, and the reason is because Alpha Centauri is a triple star. Alpha Centauri A, remember that's the nearest star to us, 4.3 light years, right? And we got to be careful when we say that. It's the nearest star system to us, all right? And it's 4.3 light years away. And that star system is composed of a component A and a component B, which are the two bright parts of the star system, the two bright star components. And then a little one, which is a red dwarf that's circling both of those at a farther distance. And that's Proxima Centauri. It's actually Proxima Centauri around which we actually found a planet circling that star. So even in systems that are binary and, as we see, trinary, you can have planets around those stars. And Proxima is a red dwarf, like I said, and it's a very low temperature star. It'll burn for trillions of years. However, A and B, the other components, aren't. They're...
Oh, wait a minute. I got a question now. You're saying, let's say you have a double or triple star system.
Yes.
Now, wouldn't the distance make a difference as far as the gravitational pull, pulling that planet toward the other? I mean, doesn't it have to be a certain distance where it can maintain the orbit around the one star?
Well, you got to remember, it's formed there, and it's formed in a place where it had already been bound to those other two stars. So it formed there, and it found its happy medium. Who knows if like 10 other planets tried to form, perhaps, and they were torn to pieces or pulled out of their orbits. We don't know. Okay, but we do know that
now,
what we see at Proxima Centauri. What we see at Proxima Centauri is a planet that's around it, and you know what? It's the closest one to us, and we still can't see the planet. It's still through inference. It's still through studying light curves and studying the wobble of the star and studying the velocity of the star and comparing the lines in its spectrum to see if it's moving away from us or toward us. That's called radial velocity. And if if the planet crosses in front of the star, between us and the star, we can actually detect that minuscule dip in the light. That's what the Kepler Space Telescope did so well. But then that just detects that the light from the star diminished a little bit. That is something interesting, because when the light diminishes around the star, it's actually could be due to something normal to the star, like sunspots on our sun, just a lot of them. And those are called star spots on other stars, ooh, hoo-ah, you know. But those star spots could be the reason why the star was dimming. So that's why when they see light dimming, they get all excited, and then they say, okay, now we gotta wait to see if it's cyclic, meaning it comes and goes. It's periodic. It comes at a certain set time. And if they're looking at a planet that takes 2 years to go around its star, well, then they're not going to get the rest of the data for 2 full years. And so then they see it again 2 years later, the expected location. Okay, this is the time when we expect to see it again. And if it's not there, then we have to assume that research was kind of wasted.
And this is how they discover exoplanets. Same kind of...
Yeah, that's what we're talking about, yep. Yeah, and so when they look for exoplanets, they actually look for that dimming around the star, and then they have to confirm it using another process, which is usually radial velocity. Radial velocity is very effective. And by the way, I just want to say something about the dome just for a minute. It's a totally different subject for a moment. You notice how my voice is about the same? I know it sounds like I'm in a small room, and I am, okay? But the thing with domes is the acoustics are such that the sound is all, no matter where you speak, the sound goes back to the same place. And that's where I have the microphone. So that's why my voice only rarely gets lower in volume, and that's because I might be looking out of the slit in the observatory, and most of the sound from my voice is leaving the observatory. If I'm talking anywhere inside the observatory, I'm spinning around right now, but it still sounds like I'm talking the same way, because the sound is bouncing all off the ceilings and the round walls and coming back to the microphone. Isn't that cool?
Now, somebody asked a question in chat, and it's specifically about Gabby Star. And why was that one so unique?
Tabby Star.
Tabby Star.
Yeah.
Why was that one so unique when it was seen? Similar to what you said about the light of the sun, or the star actually, being blocked off, and why that was so unusual in comparison to what you just mentioned. It could be sunspots, or it could be planets going in front where the light is dimmed. What made that one so unique?
That's actually a very good question. Who asked that? What's that?
Tronman63 asked.
All right. Well, you know what? That's a great and that's a very good question, Tronman, and I'll tell you why. What makes Tabby Star so unique is the fact that the dimming that we see, just like when we look for a light curve, the dimming of the star, that dimming has been going on for over 100 years, and it's been a star that's been perpetually dimming over time. The thing about this is that up to 20% of that star's brightness is going away at times. That's unheard of. There's no other object in the universe we've ever seen that can, that has light like that that's dimming. This star is doing that. I don't know why. Nobody knows why. Obviously, there's theories which say, hey, maybe it's an alien race. Maybe that's what's going on. Who knows? And that's possible. But it's all, in all likelihood, I'm taking another 3.2 second exposure here just to, that's nice. See, now that was a beautiful pulsar shot. Tabby Star is an example of what happens when someone is dedicated to finding the answers, and so when Tabitha Boyajian started to see this star and noticed that there was something around that star and that dimming, that was because of the Kepler data, the Kepler Space Telescope data. And the Kepler data ended up being very valuable, but then they went back and looked at historical imagery and historical data from that star and stars in the area, because we happen to have it. And it turned out that it was in fact dimming even more so, even up to 100 years ago. So now we don't know whether this object is actually, the dimming is caused by a natural process in the star that we just don't know about yet, or maybe it's potentially a it's potentially an alien megastructure. you know. And just for the folks in the chat to understand, you know, Bill's, you know, he's very energetic and very enthusiastic, and he loves to jump at the end of my sentence and just finish my sentences for me. He does it all the time. I've yelled at him, at Pine Bush I yelled at him incessantly for that, and anyone who knows him knows that's what he does. And I know that you probably want to just like, you know, hit him, hit me, hit both of us, but the bottom line is, it's innocent, and there's no, he's not doing any harm by it. He's just irritates me, and if I could climb through this telescope and punch him in the head, I would. I'm kidding. But the bottom line is that, you know, Tabitha Boyajian's star is one we're going to actually look at and then follow even more closely, because it's probably a star that merits further study, big time. So I think that's a very interesting star. That's what made it unique, is the fact that the dimming was going on for a lot longer than anyone realized. Now, I'm going to just spin the dome. You're not going to see anything here for a second.
Hey, those I'll just.
What's that?
I did that at his house, and I had to run like Roadrunner. Come on.
I made you. It's like meep meep, get out of here. You know, run, boy, run. You know, I'm telling you, yeah, because it was crazy. Oh, absolutely crazy. But it's all right. You know, it's Bill. What can you say? Don't mind me. I'm moving the dome. I'm looking to see if we're gonna lose our sky, and unfortunately we're going to. I don't see any way this is gonna be rescued. There's only a clear spot, kind of, sort of near our overhead. But you know what? I'm gonna, you know, go as far as I can go. And you know, if we have to look through clouds, you know, I'll see the numbers drop in the chat.
By the way, Mark, once they're very curious to see your setup in the observatory, so maybe toward the end of the stream you could detach the camera and show them.
Oh, absolutely.
Around.
Oh yeah, I'll give them a full tour of the whole place. Yeah, and you know what? I just realized I have a red light in here, and I had it off, and now it's on. And now I can see again. Holy cow! I was wondering why I couldn't see where I was going, and it's like, no wonder. I have a red light that I installed, you know, and it's just really cool. And I just want to let everybody know, I want to thank Bill, and I want to thank Paul and Keith, because they actually helped me get the setup that I'm using in here for the live stream. And it's very nice of them to take time out of their day to actually come down here, help me figure these things out. And, you know, yes, Paul and Keith and I and Bill, you know, we're creating a website together where we're actually going to have all of our streams up. And you'll be able to pick and choose which stream you want to go to, and then participate in those chats. It's going to be really cool. I just think that it's important that we, you know, also support them as well. Hopefully you can support me and you know, stick around, come to see what I'm doing as we do this. Because this has been a very, this is sort of like this is in my blood, doing this. I do, as you know, I do a lot of talks around the country. I'll be in Roswell, New Mexico in a couple weeks, doing a talk there. And then I'm going to be at Devil's Tower National Monument doing a talk at the first conference of its kind out there on extraterrestrial life out there, and that'll be kind of fun because it's also going to correspond to the 40th anniversary of the movie Close Encounters. And you know, some of you know that I work with Douglas Trumbull. Doug's the Academy Award-winning visual effects wizard who did all the effects from 2001: A Space Odyssey, Close Encounters of the Third Kind, of course, Blade Runner, the Star Trek movies, and then he did those famous movies that people love to talk about and that scare the bejesus out of them. Movies like The Andromeda Strain, which talks, that movie about a biological contagion. Doug worked on that movie too. In fact, that was his movie. And then he did with Bruce Dern. He did Silent Running, where you had Huey, Dewey, and Louie, the little robots, the little two-legged robots that walked around on the ship and took care of it. Those are the maintenance droids. Well, it turns out, and I'm sorry about the view. We're going somewhere else now. It turns out that those little maintenance droids were actually circus performers that were called double amputees. Some were missing their legs below the waist. Some were missing their legs like below the knees. and they made 3 separate little robots that these people could fit in and literally walk on their hands inside or walk on the stumps of their legs. I mean, no lie. This is the kind of thing that they did for the movies back then. All right, I'm moving. The moon is still clear, so I'm going to come back over to the moon. Now see, that's a pretty good alignment for it to actually show up like that. You can see the clouds too, and if I actually, if I move the, if I do this, you can actually see them even better. You know, how nice, we got clouds, oh boy.
Man.
But here's something I want you to notice. You notice how it doesn't look like there's any clouds over the moon, does it?
No.
But you do see them. You know, when you have this, you can actually see that those high altitude clouds moving over the moon, right?
Yep.
See, that type of stuff may always be present, and you think it's just not a good telescope that you have, or just not a good thing. You'll see this in a sec. But it might just be that you actually do have a good telescope, but you've got clouds. And with the cameras like we're using here, these ultra-sensitive cameras, we have the ability to, in a moment's notice, just like go in and out of that, you know?
Yep.
So if I zoom in now, one of the things you'll see is that the camera itself doesn't seem, in fact, the view of the moon doesn't seem to be affected by that cloud. In fact, it looks beautiful, doesn't it? It actually does look quite good. I'll zoom in one more time.
I love our cameras, Mark. I love our cameras.
You see that? Yeah. And now we actually see this, and you know, all that's missing is the beautiful music to go with this, right? But so I don't have that, but look at that. So there it is. And actually, I wanted to say something, you know, and this is something that I didn't hear Keith say on his stream, and he's free to use it if he wants to, and that is, we look at the white reflections on the rims of these craters. That's very important. That actually gives us a lot of data about the crater. And one of the things that I did when I had to teach astronomy was I actually took photographs of the moon. I actually had my students take photographs of the moon, and then we went inside and developed the photos in the darkroom. Okay, this was on film that we did that. And then when we had digital cameras, I did it with digital. And then what we did was I told them, okay, you have everything you need to calculate the diameter of the craters and even the depth of the craters. And they're like, what? You're like, what? You know, but it's true. You do. You have everything you need to calculate that information. And we get it by the angle of the sun, knowing the phase of the moon. And yes, I tolerate a little, I do tolerate a little bit of, you know, creative license. You know, first quarter, at the terminator of the moon, you know, you have to assume that the sun's elevation is low, and we have a specific value for like over here, you know, but the problem is we can't use a crater here because it's black in the center. And even if I take the camera here and I change, oh sorry, I'm zoomed, I apologize. Even if I take the camera here and I actually change the exposure and go really bright and then zoom in again, all right, like this, all right, you'll see that crater's
odd.
What?
No, you know, because I was only using the 2 zoom function, 2x. But you're zooming in using the C2 button, and you said it can go up to 15 magnification?
Yeah, at least. But I'm not talking about that. I'm talking about crater depth.
You know, I'm amazed because I didn't do this. And using the simple camera without an eyepiece, you can still zoom in on these craters.
Yes. Yes, you can.
Oh, God, it's awesome.
Yes, you can, Mr. Excitement. Now, can I finish my crater depth discussion? So, if you see, there's some craters that are a little farther away from that terminator that actually have a lightish gray bottom. This, we assume, means that where the bright crater shadow, where the bright illumination that you see is on the crater, it kind of intersects with the bottom. So you can make the assumption that that's where the bottom is, and then you can calculate the geometry of the depth of that crater. And it takes, I'm not going to lie. If you do it like you do it like real astronomers do it now, I mean, it's much quicker. But I made people do it longhand. I made them, well, not write it out on paper, but I mean, they could use calculators and computers, all the things they wanted. But what I did was, I actually made sure that what they did was to calculate the diameter of the crater at the very least, and the ones that are facing us are the only ones they could, do a circular profile of. But when they're on edge, then they could just get one dimension, that length, because some craters aren't round. Okay. In fact, on this screen right here, we're seeing craters that aren't round. I mean, there's one kind of dead center, which is round, and I'll put it right in the center, okay, and you'll see it in about 10 seconds. That's one that's actually pretty round. And that crater is actually what we would call a potentially simple to simple complex crater. Simple craters, they have various kinds. Okay, the one below that one dead center, the bigger one with a little peak in the middle, okay, with the shadow on it. That particular crater at the lower end, at the bottom of the image, that one's a complex crater. It looks like it has a flat bottom. That bottom is a result of a tremendous tumultuous demise of a meteor or asteroid that struck the moon, and lava spread out and overfilled the region in there after the impact. And where that doesn't happen, you might see rings which radiate outward from that central peak, and that's something that is very much important to study, because that tells you a lot of things. We figured out that those rings, that when we see them sticking out of craters like that, those rings actually move out about half the distance from the crater wall. And then moving over here, let's see. This is great when I'm in control of the scope. I love this. I get to move wherever I want. This is awesome. So there we see some mountains over there. Those mountain ranges, those are called highlands. And then we have this sort of empty looking area here where we just see some craters, little craters. Those are these are the Maria. But there's something I want you to see here. And if you look right in the center of the image, right here. You liking this, Bill?
No, I'm just watching it.
Good. I just want to make sure you're not falling asleep, because it can get pretty boring, right? Right in the center here, you see that there's like a round crater, but it looks as if it was filled in, doesn't it? It looks like it was filled in with something. That something, of course, was lava, and that was from another crater that's another crater that was formed on the moon, and then the lava that exuded from that impact also flooded into this crater, and it took out the rim of the crater and over flooded it, and now you have this new level set inside this crater. So you get a lot of this on the moon. You get it everywhere on the moon. And some craters, like, let's see, let me actually make it look a little better.
All right, I got a question though. How are you panning the camera, the telescope right now? Is that the camera that you're using, or?
No. This is the telescope. I have it on.
Okay.
I'm doing a micro guiding thing. I'm gonna actually, I'm gonna pull out for a second. I'm just going to change the exposure a little bit. I just want to get a little darker, because this is actually more instructional here.
So you're moving it with the pad, correct?
Yeah, I'm using my hand box, my hand control.
Okay. This way I know to do it for mine too.
Right. Now, if you notice this crater at the top there, right? That it'll show up in about 10 seconds. It's right in the center, and it looks elliptical because it's on edge, going around the edge of the moon. Do you see it yet? Is it up? Bill, you're the only one that can talk.
I'm looking, but somebody asked the question: does the moon have a molten core? Someone asked.
Actually, that's a funny question, and I'll answer it. I know the answer. I'll give you the answer. The answer is no, it doesn't have a molten core, but it does have a semi-molten or still molten outer core. And you might say, well, wait, isn't the core supposed to be the hottest part? Yes and no. It's hot. It's very hot. However, it's under a lot of pressure, And so that pressure tends to change the materials a little bit, so that that core, probably mostly made of iron in our moon, is actually solid. But the outer core still doesn't have as high pressure on it, and that core on the outside, the outer core, is actually semi-molten. Now, obviously, there's really not a big magnetic field on the moon. What that means is we don't have a process on the moon that's happening like it happens here on the Earth. Okay, that process on the Earth is a solid central core, a molten outer core, and that molten outer core is moving against the inner core, and that generates electrical currents. Those electrical currents in turn generate a magnetic field. That magnetic field in turn protects the Earth from all kinds of charged and highly dangerous radiation that could come from the sun. If our magnetic field stopped, so would life on Earth. We would be irradiated right to the ground. We wouldn't see Aurora Borealis, Northern Lights, or Southern Lights, Aurora Australis anymore. We would see them everywhere, all over, in an amorphous manner, because they wouldn't be set up. It wouldn't be doing they wouldn't be doing a swirling pattern around a pole anymore, like they do now. And then that process, that magnetic field, is why we have life on Earth. So when we look at exoplanets, the first thing we want to try and figure out is if that planet has a magnetic field. And right now, we can't. Unless we get there with a probe that can detect it. Right now, there's no way of detecting a magnetic field. But we could make an assumption based on what we see. For instance, if we go to an exoplanet and we see that, or if we look at an exoplanet, let's say with the James Webb Telescope that's going to go up next year, that telescope will be tuned and easily ready to look at atmospheres of these exoplanets. When it does that, we may actually see that a certain planet that we're looking at may actually have indications of not only water vapor, but maybe some type of strange spectral signatures in its atmosphere that would indicate that life is there. If that's the case, we would have to assume, and we would assume, that this planet also has a magnetic field. And that is something that we would determine, and be able to calculate based on that. It would be inference. Okay, we'd infer it. So it's called inference. We wouldn't be able to actually see it directly until we actually went there. So that's the kind of thing that we excuse me. That's the kind of thing that we actually do. With planets like the Earth, somebody's alarm's going off in the car.
I hear it.
It's gone now. Okay, I guess what that was. that was a good run. That wasn't a massive cloud that suddenly came in. That was actually a battery that is now dead. So that was the original battery in my camera all this time. How about that? Yeah, that's pretty good. So I'm now going to change the battery and be able to go back to this in just a sec. The nice thing about this telescope, which I really like, is that it doesn't have any issue. It doesn't have any issue with position once you actually have to get in there and change something, like a battery or something. The moon is still there. Everything is still there. I was zoomed in before, so let's go take a look and see just how far away I was. Am I in the wrong thing there? What's going on?
That's amazing how much you zoomed in.
Yeah, it was pretty cool. I'm actually going to take a photo too, by the way. So that's the photo I just took. All right, and then we go back to the live view, and in live view I can tell by bumping the camera a little bit. So that's pretty cool.
Mark, if we were viewing Jupiter again, or Saturn, like you were doing earlier,
yeah,
but using the Barlow and the eyepiece, would we be able to get a more sharper, crisper image and zoom into that with using that?
Well, let me just explain, and we're going to be overtaken by clouds soon, but I'll try and answer that. When you put a Barlow in front of a lens, that's more glass. And anytime you put more glass in front of a camera, it tends to make the image just a little bit more degraded. So it's a trade-off. That's why there's, for instance, a maximum useful power with some of these telescopes. You can't go to 7,000 times and like zoom in on one ring of Saturn, for instance. You just can't do that because you reach what's called the diffraction limit for the telescope, and that's a function of the optics. So you can only do a certain number of these tricks to see this stuff very clearly. Beyond that, you're kind of stuck doing what we're doing, and when I look at what Paul's doing and what Keith's doing, this stuff here is native to our system. Our system right now, this particular one in the John Zach Observatory. All right, so this system allows us to go zooming around the moon. We can look up and go down, okay, and do this. But it's me who's talking about it, and I'm also operating the telescope at the same time, and I'm also going through the tonight, the objects I want to view tonight, and I'm also taking care of the camera and managing the exposure of the camera and everything. So I guess maybe there's just a lot to do, and I'm glad I have 5 hands. If I didn't have 5 hands, I couldn't do this.
Now, somebody asks this question.
Went right over Bill's head, folks. Anyway, go ahead.
What's the difference? How does a radio telescope work differently than an optical telescope?
That's a great question. Now, an optical telescope and a radio telescope both look at electromagnetic spectrum, all right? But radio waves are much longer frequency than the light waves, and that we look at. And the radio waves that we look at tell us different things. And when we look inside of when we look at a radio map, for instance, of say the galaxy or another galaxy, it shows us a different thing than an optical map would show us. And that different information has different implications. For instance, to get certain features on a radio telescope image, it requires a certain amount of energy that this object may have, and it does a certain processes that would actually create the objects that we see on the radio map. Similarly, on an optical map, it's very different. We see different things in the same way. I'm looking at the moon image. There's really light clouds over it right now, so we're actually getting a degraded image. So my apologies on that. That's a pretty, just can't deny it. So a radio telescope can give us a map that befits and is due to the processes that are happening in that object that are giving off the radio waves. And the radio waves are, of course, very very powerful, and the power of these radio waves is something that gives us a lot of information about an object. We can actually deduce an awful lot about an astronomical object based on its energy spectrum that it's given off. So it's pretty cool. I'm looking to see what else might be in the clear for us right now. I'm just trying to avoid this. I'm trying to avoid the clouds. What can I say? Got any other questions out there, Bill?
Yeah, I'm looking, but I don't know how bad it is here, but it doesn't look like on the radar, like I indicated earlier, that there's much cloud cover, but I do see it. Like there's high clouds coming in your area.
Yeah, toward my, from over my head and northward and westward and southward, I have all these clouds. I have to, turn the dome a little, and it's going to change what you see because I'm going to dim out the moon a little. Yeah, you know what? I'm going to take us to one other place that I can see, which might actually be all right for now, and that's going to be another star that I want you to see because it's really cool. All right, so that's where we're going to go, and I will do it right now. And I don't, because the moon's out, because we got this other light pollution basically from the moon. We're not going to see some of the really interesting nebulous stuff associated with this star, but we will be able to see the star, and I can tell you about it because the star itself is absolutely fascinating. All right, and you notice I'm not telling you what it is yet, and that's just because I'm, I don't want you to try and start telling everybody what it is, Bill. I gotta wait for me. Just kidding.
Not that word.
I'm just kidding. All right, now this star is the brightest star in the constellation of Scorpius, the Scorpion, and it's called Antares, and we're going there now. Oops. All right, and I have my settings in the camera for the moon. I'm just going to drop it down now, and we'll start to see some stars eventually here. Once I get up to a good ASA. Actually, get the dome out of the way. Dumb of me, I apologize. All right, and now I'll just bring it in. Where are we here? Okay, there we are. Can you still hear me, Bill?
Yeah.
Okay, good. Because my mixer just toppled off the shelf it was sitting on.
I'll watch any questions, and if anybody has questions in chat, please post them, and I'll get them to Mark.
Yeah, exactly. I'm here to listen and here to help you. Don't worry, I'm here to help you. All right, let me. Maybe I can get out of that. All right, now let's do speed. We're going to increase the speed of motion a little bit. And we're going to go here. Okay. That right there is Antares. And the first thing I'll do is to show you the color. And by now, you know how I'm going to do that, right? Everybody knows by now that I'm going to show you the color by first untangling my handbox controller from the cable that is attached to the camera. That's the first thing you do. Okay, that's done. Now, the next step is to do this. Change the focus. Okay, look at that. This star is a bright orange star. And it's orange for a reason. It's actually a giant. It's a very, very big star. It's a red giant. And one of the things that is important to understand is that Antares is Alpha Scorpius. It's the brightest star in Scorpio. And it's such a big freaking star that if we put it in our solar system, it would go out past Mars in terms of its size. Wow. Yeah, that's pretty cool. Now I'll just get the focus back a little bit. And then just for fun, alright, I'm going to take a photo. I just want to see what we got out there.
And what's the distance from the Earth to this star, Mark?
This star is 550 light years actually away from us.
Oh.
So it's pretty bright. So now I'm going to go and do a ASA 32,000 3.2 second shot. So shot begins now, and for 3 seconds. All right, and then it'll come back. So you'll see it. There it is. And I'm still assuming it's a 10-second latency, Bill. Bill, are you there?
Yeah, I'm here. I was just looking at the picture.
Okay. I'm assuming it still takes about 10 seconds?
Yes.
Okay, good. Yep. Now, you can't really tell what's going on here because the moon is out and I haven't really got it optimized. But Antares sits within a cloud gas that it illuminates and excites, basically ionizing the gas around it. And this is something that's really interesting, that the process. When you've all seen the Orion Nebula, I hope the Orion Nebula is in Orion, and it's actually a very interesting place because we can actually see star birth there. We know there's stars being born there, and when these stars are being born, basically they're compressed. The gas is being compressed, and that gas that's being compressed, eventually, again being hydrogen mostly, eventually it will end up winking on, basically, and forming a new star. And that's kind of what we're seeing there. Now, Antares, though, is actually basically near the end of its life. It's a red giant star, and it's eventually going to disappear. And I'm not sure what its mass is, but it might actually it might actually go and become a supernova at some point. And the interesting thing about supernovas is that they give us a lot of the materials that are in our periodic table, and that's the thing, that we don't often recognize. Now, Antares is also a double star as well. That's the other thing, and we can't really tell that. And if I were to zoom in, I don't think we would actually see that. All right. Okay, because the separation of the stars is within the glow of Antares, so it's going to be kind of hard. And I could try focusing, a little micro focusing, but Antares is kind of low right now on the horizon, and it sort of makes it troublesome. And the worst part is that it also has an effect caused by the clouds. There's clouds right below it, which naturally are going to cause more of an issue. So that's not going to help us at all. But I think it's interesting for you to see that flickering and what's going on. That's actually real time. You're seeing that just like it's happening, and that's something that again is due to the turbulence of the atmosphere. Now, Antares being so large and also so bright has a really, really powerful stellar wind. So it actually is blowing off elements of itself out into the interstellar medium, as it is, and it's actually sometimes called the Antares Nebula. All right, because it's from there, and so there's a lot of really interesting things that go on there. So a lot of crazy properties. Now, it's the spectral class of this thing. We talked about the O stars, the B stars, the A stars like Vega. All right. Well, then there's F and G, and K and M, and that G stars are like us. We're a G2, not a G0 or a G3, but a G2, right? Kind of nearly at the beginning. And then Antares is an M star, so that's all the way down at the end. So you have O, B, A, F, G, K, M. Now, M stars are typically dim, ultra-cool dwarfs, low-temperature dwarfs. But Antares isn't a dwarf anymore. A dwarf star is the one that's doing that normal burning of hydrogen gas and making it into helium. Antares is beyond that. Antares has already bloated. It's a red supergiant, kind of like what would happen to the sun when it runs out of its hydrogen. And that's what we're seeing here. So we're seeing a star that's like that. That's why it's so big. All right.
I got a question for you.
Yeah.
If there was planets that were surrounding this sun, would we actually see it overtake? Would there be something visual that could be picked up? If it was overtaking another planet, as far as maybe an explosion, or
we wouldn't see an explosion. We would see what's called excess infrared. We look at the stars with infrared, filters, infrared light, and we have to do that in space to get the best results because infrared radiation does not like to, travel in our atmosphere very well. But it is interesting to actually consider that maybe it's possible that we might see, some type of excess infrared energy that's coming from that star that's indicating that something is actually happening at that star. Like that. And I think that's not outrageous. That's actually quite a good question, you know. I'm proud of you, Bill. I'm telling you, man. I'm proud. That's very, very proud of you for that. I mean, it's really good, you know.
I'm looking for a question. Somebody asked a question about Mars. They wanted to know about its magnetic shield. What are the ideas about why Mars lost its magnetic shield?
Magnetic field? Well, the magnetic field of Mars, I almost pulled my mixer down again. I gotta get a longer, I gotta get an extension, by the way, for my headphone. Anyway, Mars had a magnetic field. We know that because there are areas on Mars that still show magnetism in some of the areas. And so we know at one point it probably did have a magnetic field. However, that magnetic field has kind of gone away. And why would that be? Well, from our discussion earlier, talking about how magnetic fields form. They form from a solid core surrounded by a molten core, and that dynamo, that's constant dynamo of the outer core moving against the inner core, causes electric currents, which in turn cause magnetic fields. Now, Mars had one at one point probably, but it's gone now, and that basically tells us that the outer core on Mars is not as effective anymore at generating magnetic fields and electric currents. And that's kind of, you know, unfortunate, because that means that the ultraviolet radiation, that is the very powerful radiation that can disassociate, meaning rip apart water molecules in the atmosphere, isn't being stopped by anything. So all over Mars, all over the surface, the ultraviolet radiation makes it all the way to the ground, unlike on Earth where we're protected. So that being the case, the thinner atmosphere of Mars, it gets thinner and thinner and thinner over, you know, millions of years, billions of years, and to the point where it is now. It reaches an equilibrium state. And so that's where it is. And so we don't, unfortunately, have a way of actually seeing what Mars' magnetic field might have been, other than gather clues from what it is now and what we see for the residual magnetism that we see. I don't know if that is helpful. I think, you know, what that basically says is that you know, we're doing our best with what we have. I just took another 3.2 second exposure. See if we can see anything. Sometimes, you know, you pick up satellites through the field, and that's something that I always try to find, see if we can find them. I'm just waiting for some clarity here. I'm going to try something else, and I'm going to see where it is and see what we can do. Alright, we're going to go to something else right now. And we're moving. Alright, one moment as we solidify our find.
That's good night, by the way.
What?
That's good night.
Oh, why the heck is she going to bed? I know, it's England. It's late over there. I get it. Alright, let's see here. There it is, right there. Okay, you see that little faint thing in the center? You'll see it in a second. Alright, do you see that faint thing in the center?
Uh-huh.
Now, the question is, you want to say, well, what is that? And I'm going to say, let's find out. I'm going to take a quick exposure of it, 3 seconds. Alright. exposure being taken, exposure over, and now you'll see what it is in about 10 seconds. Dun, dun, dun. Check that out.
Wow.
That is, Dave Schock mentioned this earlier. This is what's called the Great Cluster in Hercules, the constellation Hercules. It's called Messier 13. There's that Messier guy again. This is one of those things that he cataloged as something to avoid. Yet this is a globular cluster of stars. Now, globular clusters are fascinating objects because they're all gravitationally bound. Now, in physics, we have something called the N-body problem. N is in Nancy. Okay, the N-body problem is a problem where you have multiple objects that you have to solve their motions for. In this case, we have this object here with thousands, tens of thousands of stars, all gravitationally interacting with each other in really exotic ways. They're kind of orbiting each other, but then as a whole, this entire buzzing cluster of stars, it looks like an exploding snowball of stars.
Yeah.
This is actually orbiting the galaxy as a whole. And these are objects that are among the earliest stars to form in our galaxy. So they're older stars. And the stars actually have very few metals in their spectrum. Now, metals, anything other than hydrogen and helium basically was called a metal. So hydrogen was around and helium was around. But then when stars exploded and did that thing like M57 where they sloughed off their outer layers and became these nebulae, that material would go into making new stars. And so later stars ended up having these other spectral signatures in their spectrum. Things like calcium, things like nitrogen, oxygen, carbon, okay? Things like lithium and stuff like that. Okay, all those other chemical elements would show up in the spectrum of later stars. All right, and when you look at something like this cluster of stars, these stars are very old. They're actually what are known as population 1 stars, and they're very metal poor. So they're among their first stars to form. And the question is, why did a cluster of stars form like this? And how come there's so many of them around our galaxy? We can go to like 10 globular, whatever you want to call them, globular clusters, in one night if we want to. They all look the same. Some are fainter, some are brighter. Actually, this is pretty much the brightest one, except for one we can't see, and that's called 47 Tucani, which is down below the horizon all the time. We don't see it from the northeast. But this is an interesting dilemma for us because we don't know, and we don't have any idea how we can, calculate the value for how these things are moving around.
I got a question for you, and this may sound like totally naive, but what's keeping them bound gravitationally to each other? Because I always thought that it has to be circling around one center body. So how are they able to stay in that cluster like that?
Well, they're doing that because they're bound to each other and they're actually moving around each other, and it is a very tough problem to solve as to how these things could actually do this. All right, but that's gravity, Now I want you to notice something, by the way. I'm sorry, Bill. Let me just show. When this comes back, you're going to see one picture I just took. But then I want you to see this. This is the live view, right? You notice how faint it looks. Okay. Now when we actually go look at what the photo we just took, look at. That's another one too. Look at that. Okay. That is a lot more extensive than this, right? You can this is the visual. You're barely scratching the surface, okay? Barely scratching the surface. So what I'm getting at is these objects most of them require a camera to really see pretty and to actually see what's really going on. So when we look at, an object that was like through a cloud, that was through a cloud. This is the one I took first before the clouds overtook it. See the difference? I mean, clouds don't bother us. Oh, yes, they do. And now you see every one of those are stars that are in this M13 globular cluster. The ones actually around the outside of it are not in it. That's in the galaxy that's within the galaxy with us. The globular cluster is actually outside the galaxy. It's called a halo object. It's outside and it's circling the galaxy from outside. It's a very odd. It's a very odd construct. These globular clusters, and no one can explain really why they exist the way they do. But isn't that cool?
Somebody wants to know what's the longest exposure you can take on the camera.
That's fully dependent on the darkness of the sky. You can take an exposure all night long if you want to. And if the camera, was in a dark sky region, then you would be able to do that. The only trouble is, the camera setting has to be on what's called B, which stands for bulb. It's a legacy term, and then you can press the shutter and hold it for as long as you want. But with a telescope, you don't want to hold the shutter down because it'll shake the telescope. This is me just touching the camera, okay, right here. All right, and you can see this star image on the left is kind of bobbling around just from me holding the camera. But there are remotes, and I have one actually. I can actually control this camera right now from my iPad and do all this work and all these photos from inside the house if I wanted to, and not even be out here in the observatory at all. But I want to be out here. I want to enjoy this. I have been, for years, I have wanted an observatory. So I have one now, and I am not going to leave. I think I'm going to stay here for good.
I'll tell you one thing, when you showed me that Play Memories app, and I started playing with it, with the camera, it is amazing. Where you can take even video, you can record from a phone app.
Tell people what you're talking about, because they don't have any idea. They don't even know what you're talking about. Tell them what you're talking about.
Well, app that you can get on the phone or iPad, where, like Mark is saying, that ties into our phone. Play Memories, and you can actually control the camera remotely. Nice. And you can take the photos, like you mentioned, or video onto a card. So it's just an amazing thing to be able to play with your camera from inside the house while it's outside, wherever it is, and be able to control it and do everything you wanted to do from an app. I think that's just awesome.
See, folks, you heard it here first. Bill is a junkie for toys, and I think it's a sickness, but I don't know if there's any cure. And of course, I'm laughing because who am I to talk? Look at what I'm doing. I'm in the middle of a big toy, okay, that I created here. So, that's true, and I understand that it's a bit crazy. But that's what it is. That's what it is. Hey, by the way, let's see. Keith's done, huh? Is it P&K imaging, space imaging, are they done for the night? Or are they still going?
I am sure he said he would be here after they're done wrapping it up over there. Hello to Rob. And there's 40 watching, and we have a lot. They're loving your stream, by the way, Mark. They're really enjoying everything that you're doing.
I hope so. I need to know what's working, what's not, so that I can make changes. Because, I didn't put this all together to make it a sort of a half-assed delivery. This is. I want this to be the best for what it does. And there's other people out there. I guess imitation is the sincerest form of flattery. And there's a guy out there that has, I said it on a P&K Spacewatch website, or I'm sorry, stream. I said I was calling it SkyTour LiveStream. Within hours, another guy comes up and says, "Watch my streams called SkyTour LiveStreams coming up." It's like, what? Somebody trying to jump in and take it for their own. And it's like, man, I guess that's flattery, right? When someone tries to steal your work. And I guess that's the sincerest form of flattery is when someone imitates you. So I guess I have to consider it as a flattering thing, kind of, sort of. I don't know. Keith would have a few things to say about that because he knows who I'm talking about. And it's just like, I don't care. Look, there's enough room in the playground for everybody. The sky doesn't belong to me or anybody. in particular. I just want to see some neat things get done, and I'd like to see some really good science get done. And most of all, I want to see some good science education get done, you know. And I'd love to have a stream with Neil deGrasse Tyson. I would love that. I would think it'd be great. You know, Bill is helping or is working on a prospect for getting me in touch with Michio Kaku, who's another guy that I would actually like to talk to at length. You know, Keith is working on the Neil deGrasse Tyson end, and I'd love to have that happen. I'd like to see that happen. I'd love to be able to, you know, go and spend time with Neil deGrasse Tyson and stream and talk with him and discuss everything that's going on. I think that'd be fun. A lot of fun. So, anyway.
I agree. Definitely. It's going to be interesting to have both of you, or like you said, Michio or Tyson on with you. It's going to be a tremendous conversation.
Yeah, and obviously, you know, I'm not trying to equate myself with Neil deGrasse Tyson or Michio Kaku, of course. They have their own individual successes they have, and there's a huge reason why they're so successful at what they've done. And I certainly wouldn't try to say that you know, I am at their level. I'm not. You know, I'm a different type of an astronomer. Oh, there's a beautiful shot. Wow, wait until you see this one. This one's even better than the first one. I just noticed that there's a clear patch of sky overhead. Alright? So, it should be coming up, and then I'm going to zoom in on it, because this is what I do to check the quality of the image. Okay? Now, I study the quality of the image. You'll see this in a second. I studied the quality of this image to actually see how the focus is and if there's any kind of trails to the stars. Now, admittedly, there's some clouds up there. All right, so this is kind of through a thin veil of clouds. But if you see that, you'll see that actually has this bright intrinsic core, which is really, really pretty. And I think that looks really nice. And then it can zoom out, of course. I also like the fact that we can do this dynamically, so you can all see this. You know, and I think that's really important to do.
It looks amazing. It does look amazing in the photo.
Yeah, it looks pretty, very pretty. So that said, let me try and look and see. I'm going to have to open the observatory door a bit, and I'm going to just look outside to see what I've got in terms of coverage and what I can do about the clouds. Oh God, that's terrible. Oh, I wish I didn't look outside. Wish I didn't look out there, folks. It just doesn't look good. I'm sorry. I wish I could. You know, that's the other thing about an observatory. When you're inside, you're only seeing out through the slit, and you can't actually see what's really going on out there. And it's like, oh no. Unfortunately, it's not very good. But I did say that I would show you the observatory, and we're probably going to wrap up the stream because the sky is just not cooperating. It's not going to be good.
Well, not for nothing. What a great way to start off your first stream and get this all rolling and doing what you're going to be doing in the future. And it's only the tip of the iceberg. It's just going to get so much better. I mean, it's going to be great.
Yeah, and you know, I'm going to thank you, and I think Amanda was helping out in the chat. I'm not sure if she is or she fell asleep or whatever, I don't know. I think that's great. I appreciate, you know, everyone's help. I'm actually going to, it's going to go black for a second because I'm actually going to take the camera out, and I'm going to take off the adapter.
And you got a lens.
And put on the lens so that I can actually show you the setup and what's going on here. I think that will be instructional. Okay, there we go.
And did I just do it again? Finish your sentence?
You did. You did indeed. Yes, you did. Okay. So, let me take this and give it a little bit of, knock this down a bit here. Hold on. Here we go. Wait, this way. Okay, now we're gonna, just a sec, I'm just gonna drop this, there we go, okay. Now what's on the screen is what I see in the, you can see you know, what's on the screen is actually what the camera sees. All right, so I don't look through the eyepiece anymore. But let me just show you around. Okay, this is the dome. Okay, you can see out through it. Oh, and there goes the little mixer again on the ground, but it didn't get broken. So we look outside and you can see the clouds that are here now and bothering us tremendously. Maybe you can't, but let me do this. But I mean, there's some breaks in the clouds, and unfortunately, you can see, you know, those breaks just aren't enough for us to be able to do anything. So we got a lot of the clouds in the way. I mean, we have stars. I mean, see, the stars are there. There's a lot of stars, but we're just not able to do what we want, unfortunately. But let me back out and show you around. Okay, this is the telescope. It's on a pier. The pier is about 150 pounds, and this pier is this steel tube you see here. It goes down to the floor. The electrical is coming up from the floor. I have power ports over here. I have USB, and I have regular power and oversized outlets for big giant wall warts. These things which actually power other things. This actually powers the telescope. Then this little unit, which we didn't use tonight, this is actually a Wi-Fi controller, for the telescope, so that I can actually connect it with Wi-Fi right to the iPad, and it would then I use the iPad to actually drive the telescope around. I didn't do that at all. I didn't do that tonight. So the telescope right now is in the looking up position where we left it. It's looking right at M13, the Messier 13 that we talked about, and that's still through the hole here. See, there's the end of the telescope. You can actually kind of see, when you go in the end here, you can actually see that there's another little spot up there. That little black dot you're seeing is actually the secondary mirror of this telescope, because this telescope uses a strange system. The light enters at the top of the telescope, up there, comes down here, bounces off the main mirror, goes back up to a smaller secondary mirror, you saw that little round dot in there, and then comes down through the hole in the mirror, which is right here at the back of the telescope, and out to the camera here. So it's what's called a folded optical path telescope, or a catadioptric, or a Schmidt-Cassegrain. It has, it's called all those things. So that is the telescope. It's on a fork mount, which is actually polar aligned. The way this works is, this is a wedge, it's called, and this is a tilt plate. This axis right here, okay, that you see going up, this angle is at my latitude, and North Star is that way exactly. So if we look up there, and if I were to spin the dome around, okay, we see clouds, unfortunately, but the North Star is actually still visible, believe it or not. It's just very, 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 very poorly visible. And if I bring this down a bit, I'll show you. Can you hear me okay in there? I'm not sure if you can hear me.
Yes.
Okay, good. So obviously, I can't even see the North Star too well right now, and that's because of the clouds that have moved in. And we still see there's a couple stars visible up above. Okay, that's Vega right there.
We're buffering, and even I am too. Something's going on with buffering. Maybe now it's better. Okay.
Okay.
We're buffering now, Mark, so I don't know if it's a signal thing, but...
Am I buffering right now?
Yes.
Oh. Okay. Well, that said then, I guess, you know, is it still buffering?
No, not now. We just have a black screen.
Okay, well, it'll change in a sec. You should be able to see my telescope again in a second. You got it?
Yep.
Telescope's there? Okay, good. Yeah, so this is, you know, by putting it on the white walls of the observatory, what's interesting is I don't have a light on in here. What's actually going on is the telescope, you know, the color is reflecting off the screen, and so that makes the whole room light up. So the whole dome is like, you know, this right here, obviously. And if I bring it up, so you see our view. I mean, it's actually really pretty. It's honestly a gorgeous view, and I just wish we could, you know, have more tonight. But all those clouds just sort of came in, all just at once. And if we spin around the other way, all right, we can look and see that there's the house, and there is the moon and Jupiter up there. And the nice thing about this camera is that we can basically turn night into day with this camera, you know, just by changing the ASA. But you have to record to do that. But that's a nice view. That's the house, and there's a quarter of a second. If I were to make this like something where I could actually take a picture, I'd do this. I'd say, all right, this is a 60th, and we'll see what that gives me. That's the image I get. All right. So, you know, you get some pretty cool images, and the camera's got some really neat stuff. As you can see, our sky is pretty well overtaken by clouds. And up there in the sky is, right there is Antares. And you can see those 3 stars, 1, 2, 3, and then Antares right there.
We're buffering again. We're buffering.
Okay. Well, I'll just let it sit here for a second. You'll see it. Okay, that's the head of the scorpion, and Antares is the eye of the scorpion, basically. So that is the observatory. That's where we're doing this, and the only thing left now that I'm going to do, which you may or may not be able to see, I'm not sure, is because I'm done for the night, I'm actually going to go out on the handset, and I'm going to go and I'm going to actually park the scope, meaning I'm actually going to move the scope to a home position. Okay, that says park scope, which you can't see. I'm going to move the scope to a home position that I use, and that will be conducive to me starting it up all over again for the next phase of the next in the next stream. It'll be perfect. So, how about that? And there we go. Okay, we're back. So anyway, my cable was a little loose. So I'm now going to park the scope. So you'll see it actually move. You'll see how the telescope moves, which is kind of cool. There we go. And it's now parked in its rest position for the evening. And then I have to put the covers on, and then I will be out of the observatory and ready to go back into the house, where I can do almost anything. Except
if it's clear tomorrow, will you be streaming again?
Yeah, I'm gonna stream every clear night I can, because I think it'll be a great idea to start introducing this to people. Now, it says the scope is parked. Turn it off. So now I'm going to turn it off, and that's this. Scope is now off. All right. So it's set, and the alignment I had will be remembered for tomorrow, and that's pretty cool. I like this. Now, that's why I like this whole this whole parking process for the scope. It's really hard to get the scope aligned properly, but I like when we can. Yeah, I want to actually show you what it really looks like in here. It's about like this in here. So I know that's a little brighter than it should be. This is more of like how I normally am in here. Right? The red light, okay, that red light looks a little bright. Okay, actually the red light itself is going to be kind of like, I'll show you, just so you know, so you can see. The red light's actually more like that. And so you find, and it's amazing, you find that your eyes adjust tremendously well to darkness, and that's what happens in here. You know, you see every detail, even though you don't see it when you first come into the observatory. It's pretty cool. So let me know what you think. This is the John Zach Memorial Observatory, and there's our last shot of the night for the moon and Venus. I'm sorry, Venus. I saw Venus this morning, actually, early. And this is, let me get that, there we go. And so this is the cloudiness of the moon. You can see it's really bad, unfortunately. And of course, I have to change the exposure settings here to make it look like, this is all handheld, I apologize, but I just want you to see it. See? Boom. And there's our moon.
We're buffering again.
Okay. Anyway, that's it. And we will come back again tomorrow if it's clear, or whichever night is clear. I'm very happy that we actually had a clear night of any kind tonight. And that was very successful for us. So I will make sure that we do the same thing again, and I'll have other objects to look at. And unfortunately, with the moon, it means that we're not going to be able to look at too many, galaxies and really cool things like that. But we will be able to see double stars, another bunch of double stars. We'll also be able to see clusters, and we didn't get to see any clusters tonight. And that was kind of intentional, because the clusters I wanted to show you were kind of near the moon, and I have to kind of wait for the moon to go to a different part of the sky to make it easier. But I think you'll appreciate it when you see them.
And I'm going to do a quick shout out to those that I show as participants in chat.
Yes, please do.
Thank you to Sherry, C&D Boy, Dapple Ben, Amanda, of course, Genghis Khan, Jonah, Ken Hancock, Nancy, of course, Keith, Pro, Rob, Robert Morningstar, Rocket Man, Rockstar, Sarah, and everybody else that has been in chat. Thank you for being here, and Mark will be back hopefully tomorrow night. And hope you enjoyed the first stream that Mark has done tonight, and looking forward to a lot more. So this is exciting, so stay tuned to a lot more streams in the near future.
Yes, give me some thumbs up if you can, and I'd like to hear from you. Let me know what you think. And if you think we're on the right track, please forgive the first stream crap that was going on here and there that was not really conducive to the stream, but I'm sure that it'll be okay. Oh, there's an interesting effect, by the way. You see that?
Duplicate. I missed duplicate. Go ahead, I'm sorry.
You see that little flashing on the screen? It's sort of like banding that's kind of bouncing.
Yeah.
Okay, so you see that now, right? That's the camera receiving data from the reflection off the screen. And the screen is flashing at a certain rate, like 60 cycles per second. But I'm capturing at 59.9904, whatever it was, frames per second, and we're getting a slightly little bit of a mismatch. You see how that banding is bouncing a little bit?
I see it.
That's for you, anyone who's still here and listening, that's physics at work here you're seeing, so it's kind of cool. Anyway, there's my Snapple. I still have to finish it. Yes. Yeah, I will. But anyway, I'm grateful that you guys stuck around. For those that did, I haven't even seen the stream. I apologize. I have not been able to see it because I'm in this, so I didn't get a chance to see what's going on. But hopefully there were enough people here to constitute, coming back and doing it again. I hope so. Anyway. Okay.
So we're all done for tonight, and again, hopefully he'll be he'll be streaming again tomorrow night. So everybody, keep an eye out, subscribe, get those alerts, do that little bell icon so you can get the alerts when he streams. And as soon as he goes live, you'll be the first one to know. So stand by. And of course, we have to mention P&K Space Imaging, who also does great stuff. And hopefully in the near future, the three of us will all be streaming on one page. We'll have it set up. And it's going to be fun.
No, hopefully about it. We're gonna.
Yeah.
I mean, we have to, because you stream wide angle sky. Keith and Paul stream Moon, Venus, Jupiter, Saturn, as appropriate. I want to stream deep sky objects and take us there. Unfortunately, tonight when we have the moon out, I can only do clusters, and then we have clouds, and I couldn't do it. And then of course the moon was in the way of some of the clusters I want to look at. So we gotta kind of move around, and we can do more really pretty double stars and show you all those colors that are really cool in there and all that. And then as Cygnus, the swan, gets higher in the sky, way up high in the sky, then we're going to find that there's a lot of star fields that are just fun to go cruising slowly through. And you actually see all these stars, the many, many thousands of stars that you just can't see with your eye, that are available to you when you actually see the star clouds, close up and personal. I mean, it's just beautiful. So, and we'll be doing a lot of that. We're going to be doing a lot of Milky Way scans and having fun, both at wider angle and and zoomed in. I'll be able to do the eyepiece projection here, which I didn't use tonight. I have it, but I was, like I said, I was disappointed with the magnification that I got. So I have to change the whole approach, change the eyepiece that I actually use. So we'll do that in the future as well. All right, and so that said, I want to thank you all, and I will officially end the stream here shortly in a couple of minutes. But again, leave me a couple of thumbs up and subscribe. Get your friends to subscribe if they haven't yet.
And Mark,
yeah,
we got to say this. Happy birthday to Amanda.
Oh, is it her birthday?
Yeah, I think it is in 6 minutes.
Wow.
Well, this is for her now because she's got the one. It's 12:54 where she is, so it's officially her birthday. So happy birthday to Amanda.
Wow, yeah, and just Amanda's 14 years old. Everybody, isn't that great?
All right, so till tomorrow night, everybody, have a great night. And again, tune into Mark's channel, P&K Space Imaging, and also, of course, Mark.
And you, Bill, yes. Bill New York Skywatcher. Look for those beautiful wide-angle shots of the sky. And don't worry, I'm going to get Bill to take that camera to a dark sky site, which is near me here, and it's actually very beautiful, and I don't own it, or else this observatory would be there, okay? But we'll do that. I'll make him do that. So now I've committed you, Bill, and you have to do it. That's what you get. That's what you get for finishing my sentences. Okay. So,
Good night, everybody.
all right. Good night, folks. I'm signing off now. We'll talk to you again.